Hello, hi, namaskar everyone. My name is Deependra and I welcome you all in this one short video of determinants. In this single video, we'll cover everything related to determinants, whether it's concepts, learnings, short techniques with a lot of previous year's questions. In this one shot, when you club this particular chapter determinants with matrices, it becomes such a lethal combination that this unit becomes the most important unit of IIT JEE mathematics. I'm not saying one of the most important, it is the most important. Every year from matrices and determinants, they ask you minimum 2 to 3 questions. And with the 3 questions, I hope you are scoring, you can add plus 12 marks to your JEE score. So the relevance, the significance is amazingly huge, and this shot is provided to you at absolutely free of cost. Along with this one shot, we will provide you the short notes, the handwritten notes, and of course the DPPs that are practice sheets. All these things are available on our PW app, link to which is already given in the description box. PW app is the app from where already millions of aspirants are preparing for different competitive exams and getting the desired success. So without further ado, let's get started with the chapter Determinants. Let us first of all understand what we'll be discussing in this chapter. So we'll begin with the determinants expansion. Different short techniques are also which will be revealed here. So stick to it this part. Then we'll talk about minors and cofactors. What are minors and cofactor and what are the different methods of finding the minors and cofactors. There also will discuss certain short techniques. Then we'll talk about the application of determinants in coordinate geometry. So some people keep on asking that, sir, what are the applications of determinants and matrices? I'll show you directly that how useful determinants are in coordinate geometry, that without learning a lot of formulae, you can apply determinants and get the results. Not just that, there are certain properties which will make the expansion of determinants very simple. We'll talk about them here. Then we have system of linear equations. So no matter what number of variables you deal with, if you are given certain equations, you can solve them, and the method, the simpler method, the easier method comes up with system of linear equations, or you may call that Cramer's rule. We'll discuss that as well. Along with this, we'll talk about system of homogeneous linear equations. Well, if there is no constant term, if the constant term is 0, how do you deal with those equations? We'll talk about the trivial and non-trivial solutions. There is always a question asked on this particular concept, system of homogeneous linear equations. Usually they ask a question based on it. Then of course, can we differentiate a determinant? Can we integrate a determinant? Can we apply summation on determinants? That is also we'll be discussing in this part of this particular video. So a complete revision of this chapter is one shot is being done. Stick to it, watch it completely, revise all your concepts, and the video is right there in front of you, and I hope we can straight away get started with this part. So when you talk about determinants, determinants are simply a square matrix value. So square matrix has its own elements, but determinant is basically a number which you take, which you get after applying certain number of operations on a square matrix. Although what is a matrix, what is a square matrix, that is what we'll discuss later. But how do you find the value? How do you find the determinant of a square matrix? That is what we'll discuss in this particular part. So determinant is a very simple expression where you have n number of columns and n number of rows. So number of rows and number of columns are same, and when you have number of rows and number of columns are same, which means n into n number of elements are arranged there. Usually as per your syllabus, you will deal with either a determinant of order 1 by 1 or a determinant of order 2 by 2 or a determinant of order 3 by 3. Now what do I mean by a determinant of order 1 by 1? There will be one column and one row, which means there will be only one element. If there is a determinant of 2 by 2, so 2 rows and 2 columns, which means there will be 4 elements. If I talk about a determinant of order 3 by 3, which means there will be 3 rows and 3 columns, which means total 9 elements will be there in that determinant. I hope this part is very well understood by you all. Determinants are usually denoted by capital D or delta as well. So such letters are reserved for determinants. Well, you can actually, identify their positions as well, the positions of elements. For example, how do we begin with? For example, this here is the first row, right? This here is the second row. This here is the third row. Not just that, you have columns as well. So this is column 1, this is column 2, this is column 3, which are denoted by C1, C2 and C3. So this I think is all about determinant as of now. But when you want to mention something related to determinant, for example, there is a 3 by 3 determinant, right? So this is a 3 by 3 determinant. And if I want to position an element, so how do I begin with? Let's say if I'm calling it A11, so what does it mean? It means the element of first row and first column. So the first digit here represents, the first number here represents the row and the second number here represents the column. Same, if I were to write A12 here, so this means A12 is the element positioned at first row and second column. I hope this makes complete sense. Similarly, if I write A13, first row, third column. Now, can you help me in locating A32? So A32 means third row, second column. If I were to ask you A21, so second row, first column. Can you help me with A23? I hope you know second row, third column, right? Similarly, you would have written second row, second column, A22, third row, third column, A33, third row, first column, A31. So this is how elements are positioned in a standard determinant. So this is what I'm trying to make you understand. Always remember, determinants are always square in shape, which means 3 by 3, 2 by 2, 1 by 1, 4 by 4, although you deal up to 3 by 3 only as per your syllabus. Now, how do we proceed further? What additional details we need to deal with? There is a sign scheme. So whenever we are expanding a determinant, we have to follow a certain sign scheme. Well, there is a logic behind this sign scheme, which you need to learn. And if you have learned that, you need not learn the different sign schemes for different level of determinants. The sign scheme is very simple, students. Let's say I have this determinant where the positions are A11, then this element is A12, this element is A13, then we have this A21, A22, then this is A23, then you have A31, then you have A32, and there you have A33, right? Now, sign scheme is a very simple concept. All you need to do is add its row and column. So index, right? So here for this A11, if I were to ask its a sign, the sign scheme, as per the sign scheme, what sign should appear here? It will be 1 plus 1. 1 plus 1 is 2. Tell me 2 is even or odd. If 2 is even, I'll use a plus sign. If 2 is odd, I'll use a negative sign. Why am I doing it? Because actually, it comes from the concept of cofactors and minors, which we'll discuss later. But as of now, I want to discuss the sign scheme with you because I want you to learn the expansion of determinants. So what I'm trying to make you understand is that add this index, the number of row and the number of column. And if it is odd, put a negative sign. If it is even, put a positive sign. I hope you're realizing. If I were to decode its sign scheme, it will be very simple. 1 plus 1, 2. 2 means even. The sign will be here plus. While expanding the determinant, I'll use a plus sign with this first element. Here, 2 plus 1, 3, which is odd. Odd means negative. Then I have 3 plus 1, 4. 4 means even, positive. Then you have 2 plus 1, which is 3. 3 means odd, negative. 2 plus 2, 4, even, positive. Then you have 2 plus 3, 5, odd, negative. So I hope you are getting this logic very clearly. 3 plus 1, which is 4, positive. 3 plus 2, 5, which is odd, negative. 3 plus 3, 6, which is even, positive. For a 3 by 3 matrix, this can be learnt. For a 3 by 3 determinant, it can be learnt plus minus plus, minus plus minus, plus minus plus. So they keep on appearing alternatively. Plus is what you begin with, and then minus plus, minus plus, minus plus is what you keep on writing. But let's say if it is a 2 by 2 determinant, if it is a 2 by 2 determinant, then can you help me with the positions? The positions are very simple. First element will be A11, then the second element will be A12, third element will be A21, and the fourth element will be A22. For this, if I were to write the sign scheme will be very simple. I hope you understand. A11, 1 plus 1 is 2. This means positive. 21 is 3, which means negative. 21 is again negative. But here 22 is even, which is positive. So for a 2 by 2, plus minus minus plus is going to be the sign scheme. So order 2 and order 3 are sufficient for you. And this is the sign scheme we follow while expanding a determinant. So what is the expansion of a determinant? How do you do it? Well, that we'll discuss later. But what is the sign scheme that needs to be followed while expanding a determinant? That idea I'm trying to give you here. Although while discussing the chapter matrix, we'll study cofactor and minors, and there we'll study determinants expansion again, but there we'll discuss it in a logical format. But whatever is needed to be done without that logical explanation, I'm trying to give you here that directly this is how you can remember the sign scheme for the expansion of determinants. Now, how do I proceed further? Let's take the example of a 2 by 2 determinant and how do we expand it. So let us learn these simple expansions so that they can be utilized in these chapters, different chapters where this concept or this chapter determinants is basically utilized. For example, if I'm given a 2 by 2 determinant, so how do we expand it? The idea is very simple. If I'm given a1, b1, a2, b2, there is a determinant 2 by 2 and it has its own elements. So what I'll do is I'll simply expand it a1 into b2, that will be my first term, minus a2 into b1, that will be my second term here, b1 a2. So that will simply be the expansion of a 2 by 2 determinant. In a very simpler language, students, if I were to ask you 2 3 minus 1 5, can you help me with its expansion? I hope most of you can very easily do this. The expansion will be pretty simple. 5 into 2 will be 10. Then I'll use a negative sign. Then I'll have 3 into minus 1. It will be minus 3. So I'll use minus 3 here. So 10 minus minus 3 is 13. So this is the value of this determinant, let's say, which is denoted by capital D. So always remember, matrix is a collection of elements which does not have a certain value, but determinant has a fixed numerical value. That is the major difference between matrices and determinants. Although matrices can be of any order, but when it comes to determinant, they are supposed to be square. I hope you are learning it very clearly. So I hope you have understood how do we expand a 2 by 2 determinant. If that part is understood, let us go ahead further with the expansion of a 3 by 3 determinant. So how do you expand a 3 by 3 determinant? Let us learn that. Well, first of all, you need to understand whenever you're given a 3 by 3 determinant, you can expand it with respect to any row or any column. I repeat, you have the liberty to choose the row or the column as per your mindset. Whichever row, whichever column you want to expand it with, you can do that. But when you do that, there are certain things which you are supposed to follow. For example, let's say for a while, I am given these three elements a1, b1, c1, a2, b2, c2, a3, b3, c3. So these are the three elements we are given. So these dots are definitely not there. So you should simply avoid or not look at these three dots here. So a1, b1, c1, a2, b2, c2 and a3, b3, c3 are the 9 elements of this determinant. Now how do we expand it? Let's say I am willing to expand it with respect to the first row. Now, how do we expand it? So, first of all, write these three elements of this first row. Which three elements, students? The three elements of the first row are A1, B1 and C1. So, I have taken A1 here, I have taken B1 here and I have taken C1 here. Now, before A1, B1 and C1, I'll use that sign scheme. Which sign scheme? Which we have just learned. So, before A1, I hope you know, we have already discussed for a 3 by 3 determinant, it should be plus, minus, plus, right? In the first row, we have plus, minus, plus. So, before A1, I'll use a plus sign. Before B1, I'll use a minus sign. And before C1, I'll use a plus sign. But with A1, B1 and C1, there is another factor which is needed to be brought into picture. What is that? Now, pay attention to it very clearly. With A1, I am writing something. Now, what is that? With A1, what I have done is I have eliminated the row and the column which A1 belongs to, and then I'm left with certain elements B2, C2, B3, C3. So I'll be taking the determinant of B2, C2 and B3, C3. Did you get that part? Now, when you talk about B1, which factor is supposed to be brought here? So with B1, remove the column B1, remove the row which contains B1, and then you're left with A2, C2, A3, C3. So you're supposed to take the determinant of A2, C2 and A3, C3. That is what you're supposed to do. Then the third element, which was C1. So remove the column which contains C1, remove the row which contains C1. What are you left with? A2, B2, A3, B3. Take the determinant of A2, B2 and A3, B3 and multiply it with C1. Well, whatever result you get from here will be the expansion of this particular determinant. Sir, are you trying to say that no matter with respect to whichever row or whichever column we expand it, it will generate the same result? Trust me, it will. If you don't trust me, have your own time, take your own time, expand it with respect to whichever row or column you want to. Choose any row, any column, do this operation, and after all the calculation, you'll get the same result. The result which is written over here. Although this result is not needed to be learned, what is needed to be understood is that how do you expand a 3 by 3 determinant with respect to any column, any row. All you need to do is take care of two things. One, sign scheme. Second, the removal of the column and the row, whichever element you are taking here as per the row or the column, whichever you are with respect to expanding it. I hope this part is very well understood by you all. Well, with that, if you have understood the expansion of the determinant, we have a shortcut here. We have a short technique here. Expansion of determinant is perfectly fine. You should use that. You can adapt that. You can have that. But Sarrus was a mathematician. He developed a rule for expansion of mathematics in a more simpler format. Well, I'll explain this rule first of all, but you need to understand how does it get applied. We had the determinant A1, B1, C1, A2, B2, C2, A3, B3, C3. Sarrus said, repeat the first two rows, which means A1, B1, C1, A1, B1, C1, I'll be writing again. So here I have again, rewritten A1, B1, C1. And then second row as well. So second row was A2, B2, C2. So that row also we have written here. So we had three rows. I have repeated the first two rows below the third row. So I am having a total 5 rows. Now what you do is begin with the principal diagonal elements. So take the product of this diagonal here, which will be A1, B2, C3. I hope there is a small correction here. This should have been A1, B2, C3. I hope you can see this, A1, B2, C3. Then you are supposed to take the product of, second principal diagonal elements, which is A2, B3, C1. So there you have A2, B3, C1. And then you take the product of these three elements, which is A3, B1, C2, and then take the sum of these three products. Let's call that sum as P for a while. I hope there is no confusion so far. Well, then what are we supposed to do next? Now let's go to the non-principal diagonal elements. Which one? This one. A3, B2, C1. So we have first product A3, B2, C1. Then we take the next product A1, B3, C2. So A1, B3, C2. Then we take the third product A2, B1, C3, which is A2, B1, C3, which I am writing here A2, B1 and C3, right? And thereafter getting this required product, you simply add these three products, which I'm calling to be N. Let's say that sum is N. So this sum was P, that sum was N. Next thing is very simple. Next thing is very easy. Let's say the determinant was delta. So the value of this determinant will be this sum P minus this sum N, and that will be the value of the determinant. If you got confused by this explanation, if you are thinking that, sir, that standard method of expansion of determinant is more simpler for us, use that. But I'll try to demonstrate this method right there in front of you with an example so that you get more clarity that no, this is even simpler. This calculation is eventually needed to be done. You are supposed to do it no matter whatever you do. But trust me, this is a little faster. How? Let's have a look at that. Let's say this is the determinant 3, 2, 5, 9, minus 1, 4, 3, 2, 3, minus 5. This needs to be expanded. One of the methods is choose any row, any column, use the sign scheme and apply the formula which we have learnt. Perfectly fine, you know that. Sarrus rule, can that be thought of? Yes. How? I'll write 3, 2, 5 and then 9, minus 1, 4. The first two rows are to be repeated. Now the logic is very simple, students. What is the logic here? I'll multiply first of all 3, 1 and minus 5. I hope you know that. So the product of 3, 1 and minus 5 will be how much? 5 minus 5 into minus 1, which is 5. 5 into 3 is 15. So first product we have attained. I'm really sorry. First product we have attained is it is 15, right? Now, next, what you're supposed to do is the next diagonal 9 into 3 into 5. I hope you're getting it very clearly. So 9 into 3 into 5, which is 5 into 3, 15. And 15 into 9 is, I think, 135. So I'll be writing the next product, which is 135. Correct me if I'm wrong. So 15 into 9 is 135. I'll take the next diagonals product. The next diagonal will be 2, 2, 4. Can you see that? So 2 into 2 into 4, what would that be? I hope you can see 2 into 2, 4, 4 into 4, 16. So the next product will be 16. What am I supposed to do? Take the sum of these three products, which I have already done. From this product, I'm supposed to subtract sum of the other three products. Which are the other three products, students? Well, first one will be 5 minus 1 and 2. Can you see that? So 5 minus 1 and 2. So 5 into 2, 10. 10 into minus 1, minus 10. Then the next product will be this 3, 3, 4. Can you see that? So 3 into 3 is basically 9, and 9 into 4 is 36 plus 36. Then I'm supposed to take the final product, which is 9, 2 and minus 5. I hope there is no confusion on that. So yes, 5 into 2 is 10, minus 10 into 9 is minus 90. So minus 90 is something which you can do very easily. I hope the job is done. This is your P, this is your N, and from P, if you subtract N, you will get the value of delta, which I'm sure you can do this part by yourself. That calculation is not the tougher part, but the part which I'm trying to make you understand is that how do you apply the Sarrus rule? Repeat the first two rows, principal diagonal and then non-principal diagonal, and then their difference from principal to non-principal. That's how simple it is. Did you understand the Sarrus rule, students? Can I proceed further from here? Well, if you understood the Sarrus rule, there are certain observations which you should remember. Trust me, in JEE Mains and Advanced, questions are still being asked based on these two properties which I'm going to demonstrate or show. You should remember this as a result. You should remember this as a result. If you remember this as a result, you will directly apply these results in the examination and you will get the answer at your fingertips. You need not solve anything. So what are these results? Let's have a look at them. First result says that if x1, x2, x3 are in AP, so if there is an arithmetic progression, and from this arithmetic progression, elements are arranged. How are they arranged? Let's say three elements are chosen, let's say x1, x2, x3. Then n distance away from x1, xn plus 1, xn plus 2, xn plus 3. Three more elements are chosen. Then further n distance away from xn plus 1, x2n plus 1, x2n plus 2 and x2n plus 3. These three more elements are chosen. Let's say, to make you understand it more clearly, I am writing an AP. Let's say the AP has 2 plus 3, 5, 5 plus 3, 8, 8 plus 3, 11, 11 plus 3, 14, 14 plus 3, 17, 17 plus 3 is 20, then 23, then 26. These are the certain elements of an AP, right? Now, if I create a determinant of this AP, so let's say I write first of all 2, 5 and 8, then I write 11, 14 and then 17, and then I write 20, 23 or 26. Not just that, let's say even if I further have written some more elements by skipping this part, let's say instead of this 11, 14 and 17, let's say if I have taken 20, 23 and 26, so 20, 23 and 26. Then further in this AP, the next three elements would have been 29, then you would have 32, then you would have 35. Then after further by skipping this set of three elements, you would have had 35 plus 3, which is 38, then 41, then 44. So even if you are writing this particular set, 38, 41, 44. So what have I done? I have simply taken the first three elements, then I have skipped the next three elements, then I have chosen another set of three elements, then again I have skipped the next set of three elements, then I have chosen another set of three elements. I hope you got this part very clearly. So if you are having a systematic pattern here that you have chosen a certain number of elements, you have skipped a certain number of elements, then you have again chosen three number of elements, then again you have skipped those number of elements which you have skipped previously, and you again choose three number of elements. And if you take the determinant of this expression, if you take the determinant of this particular expression, the determinant here will be 0. That's what I'm trying to make you understand. If you don't believe me, expand it, you will get the result. Just ensure that I have written the AP properly. In case if I have missed anything, if I have written any number incorrectly, then it may be wrong, but I am sure I have written all the numbers correctly. So yes, it will give you a value 0. All I'm trying to make you understand is if a determinant contains all the terms of an AP with a proper distance, the distance is maintained. First row was taken, then with second row I have taken a certain distance, and with third row I have taken the same certain distance. Well, in that case this determinant will be 0. That's the first property. If you have a determinant containing the terms in AP with same certain amount of distances between rows or columns, then it will have its value 0. Always remember this as a result. The moment you see terms in AP in a determinant, write its value as 0. But it should follow that certain condition which we have learnt or understood here. I hope this part is very well understood by you all and you will remember this particular result. This result is very widely used and it is very intuitively applied by a lot of students directly. So if you have this result, if you keep this result in your mind, apply this directly whenever you see a determinant containing the terms in AP. Always use this, right? Once you have learned this particular formula, let's talk a little more variants of this particular formula. Let's say AX1, AX2, AX3 are in GP. I repeat, AX1, AX2, sorry, A to the power X1, A to the power X2, A to the power X3 are in GP. So in sequence and series, we'll discuss this particular formula that if there are certain terms, let's say these terms only, AX1, A to the power X2, A to the power X3, if they are in GP, and if you take logarithm of these terms, if you take logarithm of all of these terms, let's say ln of A to the power X1, then you have ln of A to the power X2, then you have ln of A to the power X3. Then if there are certain terms given to you which are in GP, and if you take logarithm of all of those terms, then those terms get converted into an AP. So these terms will be an AP. The proof we'll discuss while discussing the chapter sequence and series, which we'll definitely discuss after matrices. But what you need to understand here is that if certain number of terms are given in a GP, then their logarithms will be in an AP. Did you get this particular part? So here what I'm trying to make you understand is we know that there is a property log of m to the power n is always n log of m, where m should be a positive number. Right. Now, what I'm trying to make you understand is that can we use that same property here? So x1 can be brought to the front. So x1 times ln A. There you have x2. There you have x2 times ln A. There you have x3 times ln A. And this is given to be in an AP. Now, please understand there will be a property which we'll discuss that if an AP has x1 ln A, x2 ln A, x3 ln A, and if I divide it by a certain number, if I multiply it by a certain number, then also it will remain an AP. If I divide all the terms of an AP, if I multiply all the terms of an AP by a certain number, it will still remain an AP. What does it mean? That if I divide it by ln A, ln A, ln A in all the terms, I'll be left with x1, x2, x3, and this will still form an AP. So what I'm trying to make you understand is a very simple concept, that I am given a to the power x1, a to the power x2, a to the power x3 and so on in a GP. So from here we can very clearly see that x1, x2, x3 and so on will form an AP. Did you get that part? These properties we'll discuss while discussing the chapter sequence and series. Let me get back to the discussion we were having here. If I am told that a to the power x1, a to the power x2, a to the power x3 are in GP, so can I say the powers here x1, x2, x3 will be in AP. And if x1, x2, x3 are in an AP, then this property still holds true. So this property holds true in two cases. Which two cases? First case, when it is directly said that x1, x2, x3 and so on are in AP, or the second case when a to the power x1, a to the power x2, a to the power x3 are in GP. In that case, we can conclude that x1, x2, x3 and so on will be in AP and the same property will fall. I hope you are getting it very clearly. Not just that, this second property is again an extension of the property which we have just discussed. How and why? Let's have a look at that. If I am told that a1, a2, a3 are in GP, we have already discussed if a1, a2, a3 and so on are in GP, then logarithm of those numbers will be in AP. So log of a1, log of a2, log of a3 or whatever sequence of number you pick from them. whatever sequence of number you pick from them, what I have done is an plus 1, an plus 2. Consecutive terms I have taken an plus 3, an plus 4, an plus 5. Then an plus 6, an plus 7, an plus 8. So these are the 3 consecutive terms on AP. Then another 3 consecutive terms of the same AP. Then another 3 consecutive terms of the same AP with the same difference, because we haven't taken any difference. We have taken straight 9, terms of an AP. So yes, when this again comes into picture, these are the terms of an AP. 3 terms, then another 3 terms, then another 3 terms with the same difference, where the difference is 0 here. The same property is being applied. And if this property is being seen here, this determinant also will have the value 0. Are you getting this part very clearly, students, that if in a determinant terms are given in AP, then its value is 0. That's the point I'm trying to make you understand in a very simple language, and I hope you will remember this as a result. Why am I constantly asking you to remember this as a result? Because in the examination hall, you will see such questions where such property will be applied in different questions. Now, let us proceed further, where we'll discuss the next concept, where I'll talk about minors and cofactors. Now you will understand it more clearly that what was sign scheme that I was talking about. But before studying minor and cofactor, we were supposed to learn the expansion of a determinant, and that's why I had to make you understand the sign scheme. But where did that sign scheme come from? We'll be discussing that part here with the concept of minors and cofactors. It's a very simple concept, students. You need not bother much with this particular concept. I'll explain it with a very simple example. Let's say I have a 2 by 2 matrix. Let's say 2, -3, 4, and let's say 1. Let's say this is a determinant, right? And this determinant has certain elements. I am asking you to write the minors of different elements. For example, I'm asking you to write the minor of 2. Then I'm asking you to write the minor of -3. Then I'm asking you to write the minor of 4. And then I'm asking you to write the minor of 1. So how do we do that? The concept of minors is very simple, students. Very simple. Remember this. Minor of 2 is needed to be written. Remove the row and column which contain 2. So 2 is contained by first row and first column. What are we left with? We are left with 1. So the minor of 2 will be 1. As simple as that. Nothing much is needed to be said or done. Did you get that part, students? Now, when you talk about the second part, minor of -3, I hope nothing needs to be said. Minor of -3. -3, second column, first row. What are we left with? 4. So here it should be 4. Can you see that? Can you visualize it? Now, what about minor of 4? Minor of 4 will be remove this row, remove this column. What am I left with? -3. So this will be -3. What will be the minor of 1? Minor of 1 will be remove this column, remove this row. You are left with 2. So here this is 2. This is all about minor and cofactors. Easy, I think it was. Very simple. If you understand the basics, you can very easily crack minors and cofactors. Along with this, what you need to understand is this, I think, was all about minors. Along with this, I want you to understand cofactors as well. Now, where does cofactor come from? Cofactor is basically an extension of minor only. If you implement the sign scheme we have discussed on minors, you will start getting cofactors. What did I just say? Have these minors here. Let's say I'm asking you cofactor of 2, right? Then I may ask you cofactor of -3. Then I may ask you cofactor of 4. Then I'd like to ask you the cofactor of 1, right? So how will you find the cofactors of 2, -3, 4 and 1? The idea is very simple, students. First of all, write the minors. So what are the minors? 1, 4, -3 and 2. So 1, 4, -3 and 2. So minors will be there with cofactors, but cofactor. So a cofactor will be there. That will be the sign scheme we are supposed to follow. What does it mean? Look at the position of 2. Where is this 2 positioned? 2 is positioned, the position of 2 is 1, 1. First row, first column. I hope you can see. If you are getting it confused, then A11, A12, A21 and A22. So the position of 2 here is 1, 1. 1, 1 means 1 plus 1. What is 1 plus 1? All you need to do is put this sign here. minus 1 to the power 1 plus 1. That is what you do with the cofactors. That's exactly what I'm trying to make you understand. That if 1 plus 1 is even, you put the positive sign. Similarly here, before minus 3, before this 4, minus 1 raised to the power is minus 3, right? 1, 2. 1 plus 2. 1 plus 2 is 3. So there will be a negative sign. Before minus 3, what am I supposed to put? 4. 4 was 2, 1. The position was 2, 1. 2, 1 means 2 plus 1, right? What about this 2? Again, minus 1 to the power. The position of 2 was 2, 2. Sorry. The position of 1. The position of 1 was 2, 2. 2, 2 means this is 2 plus 2. I am not asking you to do all this, nor you're supposed to do this. Just look at the position and its sign, whether it is even or odd, and on the basis of that you can decide its sign. See, 1 plus 1 was 2, which means even, use plus sign. So you need not do this thing. You can directly write plus 1 here. I hope you are getting it very clearly. 1 plus 2, the position of minus 3 is 1 plus 2, that is odd. 1 plus 2 is 3, which is odd. Odd means negative. So it should be minus 4 here. Similarly, when you talk about the position of 4, the position of 4 is 2 plus 1. 2, 2, 1, which is 2 plus 1, which is again 3, which is odd. So I'm supposed to use negative. Negative before minus 3 will be plus 3. I hope there is no confusion on this. And again, here, the minor was 2, but position of 1 was 2, 2. 2 means 2 plus 2, which is 4, which means plus sign. So it should be plus 1. So these are the cofactors of these elements. So if I were to write the minor of this determinant, I repeat, the minor of this determinant. So the minor of this determinant will be, see, the minor of 2 is 1. The minor of minus 3 is 4. The minor of 4 is minus 3. And the minor of 1 is 2. Did you get that? But let's say I am asking you to write the cofactor. Let's say this determinant was, let's say, D. So if I'm asking you to write the cofactor of D, the cofactor determinant of D, what will you write? Cofactor of 2. Cofactor of 2 was plus 1. Cofactor of minus 3. Cofactor of minus 3 was minus 4. Cofactor of 4. Cofactor of 4 was 3. And then cofactor of 1. Cofactor of 1 was 1. Now I am asking you to pay attention to this very clearly, that how did we get this? See, we had 2 minus 3, 4, 1. So all you need to do is swap these terms by, see, 2, 1 got swapped here. If I talk about writing the cofactor or minor directly, can we do that? In a 2 by 2, you can directly write the minor and cofactor without doing all this. I hope while I was doing all this, somebody might have noticed that no sir, you need not do all this. You can very easily write minor and cofactor with some simple observations. What are those simple observations? See, this 2 and 1 were supposed to be interchanged. Can you see that? 2, 1, 1, 2. So they are interchanged. And then, I'm really sorry. And then the next part was that this minus 3 and minus 3 and plus 4 were supposed to be interchanged. You can see minus 3 and 4. And that's how you write the minor. So if minor of A11, A12, A21 and A22 is asked, what will it be, students? You will simply interchange A11 with A22. So A22 will come here, A11 will come here, and then you will interchange A12 by A21. So here I'll have A21 and there I'll have A12. That's how you write the minor. That's how simple it is. Now, how will I write the cofactor? That's even simpler. Why? Because you know the positions. Because of the positions, you know the sign scheme. And sign scheme, when applied on the minor, will make it a cofactor. I hope you are getting it. So, here, if I had 1, 4, minus 3 and 2 as the minor, which I have attained, see, this position is 1, 1, which is plus. This position is 1, 2, which is minus. This position is 2, 1, which is minus. So minus of minus 3 is 3. This position is 2, 2, which is plus, I hope you are getting it. So writing cofactor is easy. It is not tough. I think I have made a mistake here. I'm supposed to write a 2 here, which mistakenly I have written as a 1. So I'm sorry, I did not notice this part. I think it was supposed to be 2. Right, that is a mistake I think I have committed. I am really sorry. This 2 was supposed to be here, so I should have written a 2 here. So that is a small error. I didn't notice that part, but I hope you are able to understand this particular portion. How are we doing it? How are you supposed to follow such results with such delicacy? this particular error, I hope you must have noticed. Mistakenly, I have written 1 here, which was supposed to be 2. But rest of the part is, I hope, very well understood by you all. No confusion on that. Now, proceeding further, let's talk about this minor and cofactor, which we have already discussed, that how do you decide a minor, how do you decide a cofactor, and then now discuss some important results related to cofactors. Now, what are those results? Let's have a look at that. Before we discuss how do you find the cofactors or results based on cofactors, let us discuss one more thing, that how do you find the cofactors of a 3 by 3 determinants. So let's take an example on that as well. Then we'll talk about this particular part. Please understand, let's say I have basically a determinant. Let's say A11, A12, A13. Then the next set of elements will be A21, A22, then A23. Then the next set of elements will be A31, A32 and A33, right, students? Now, what do we do next? The part is very simple. I am asking you to find the cofactor of any element. I'll not be able to do, or I'll not be doing finding cofactors of all the 9 elements. I'll just show you some 2-3 elements and then you'll get the idea how to do it. So, for example, let's say I am finding the cofactors of the second row. I am finding the cofactors of the second row, right? So, let's say the second row's cofactors are what we are trying to find. Please understand, cofactors of all the elements can be found, but I'm showing you the cofactors of these 3 elements only. Any 3, any 9, any element you can take the cofactors of, but these 3 I'm depicting or demonstrating here. If I begin with A21, let's say I want to write the cofactor of A21, right? So how do we do that? So first of all, before proceeding with the cofactor, write its minor. You know how to write the minor? To write the minor, what you need to do is simply remove the row in the column which contains A21. So A21 is contained by second row and first column. So if I remove them, what will I be left with? I think I'll be left with 4 elements. I will be left with 4 elements, A12, A13, A32, A33. So I'll write this determinant here. So I'll write this determinant here, which will be A12, then I have A13, then we have A32, and then we have A33. But mind you, students, this is not the cofactor. This is the minor. Now, how do I write the cofactor? To write the cofactor, A21. What is the position of A21? 2, 1, second row, first column. So 2 plus 1 is 3, which is odd. So if it is odd, I hope you're realizing I'm supposed to put a negative sign here. So this part was minor, but when minor was put with the sign scheme method we follow, then it becomes a cofactor. Did you get that part? Now let's write the cofactor of A22. So how will you write the cofactor of A22? So to write the cofactor of A22, I'll use this simple method. First of all, let's write the minor of A22. So minor of A22 means what? Remove the column A22 contains, remove the row which is contained by A22. So I think second row, second column. So 4 elements I'll be left with is A11, A13, A31, A33. So that will be the minor. So the minor will be A11, the determinant A11, A13, then you have A31, and then you have A33. So that's the minor. But here I'm supposed to put the sign as well because I'm wanting to write the cofactor. Well, in that case, cofactor will be A22. The position is second row, second column, 2, 2. 2 plus 2 is 4, even, which means I'm supposed to use a plus sign. So the value of this determinant here will be the cofactor of A22, right? Next, let us write the cofactor of A23. Again, I hope you can see it very clearly now. Column and row. So third column, second row, what am I left with? I am left with A11, A12 here, and here A31 and A32 here. Well, again, I'm supposed to put a sign here. Which sign? A23, 2 plus 3, 5, which is odd, so a negative sign will appear here. So I hope this part is very easily understandable. How did we get this? How are we using it? Let's say the cofactor A21, is denoted by C21, right? Let's say the cofactor A22 is denoted by C22. Let's say the cofactor A23 is denoted by C23. So these are the cofactors. Well, now comes a very important conclusion. The conclusion says that if you take any row or any column, let's say I have taken the second row. So whatever I taken, I have taken the second row. And if you take the sum of any row or any column with their corresponding cofactors. For example, I have chosen these three elements of second row, A21, A22, A23. And if I multiply A21 with its cofactor, which is C21, if I multiply A22 with its cofactor C22, if I multiply A23 with its cofactor C23, and if I take this sum, which sum I'm talking about, students? I am saying A21 into C21 plus A22 into C22 plus A23 into C23. Then I hope some of you must be realizing that this is nothing but the value of the determinant. Did you notice that coming, students? So this is nothing but the value of this particular determinant, if I were to mention that. So I hope you are realizing that determinant can be expanded with respect to any row or any column. That's exactly what I'm trying to say here. You choose any row, any column, and then multiply those elements of whichever row, whichever column you have chosen with their corresponding cofactors. And when you take that sum, it will turn out to be the value of the determinant. That's exactly what I'm willing to discuss in this next part of the video, where I'm saying that this is a very crucial or important result on the cofactors. Any row, any column can be chosen, and when that row or column is multiplied, when the elements of that row or that column are multiplied with their corresponding cofactors, you will get the value of the determinant. Which means whatever row or whatever column you choose and you multiply the elements of that row or that column with their respective cofactors, it will always generate the same value. It will always give you the value of the determinant. What does it mean? It means that the value of the determinant remains same no matter with respect to whichever row or column you expand it. Are you understanding this part? This part we have been constantly mentioning since the beginning of this video, that determinants can be expanded with whichever row, whichever column you wish to. And the value of the determinant will always remain same. It will always come out to be the same value. But you need to follow the standard process, the right process. Then only you'll have the same value, right? Now, let us talk one more very interesting property. Let us talk about another very interesting result. Sir, what if I multiply the elements of any row or any column with respect to other row or other column with the cofactors of any other row or any other column? Well, in that case, the value of the determinant will be 0. What I'm trying to say here is that can be understood with more clarity with this, that let's say I have chosen A11, A12, A13. These are the three elements of the first row, A11, A12 and A13. But I have chosen the cofactors of the second row, C21, C22 and C23. Well, the sum of the product of these elements with these cofactors will be 0. This is always true for any determinant. We are not proving these properties right now since it is a one shot. I'm directly giving you the results which you should remember and apply in the questions. So what did I say? If you take any row or any column, but if you multiply the elements of that row or that column with some other row or other column's cofactors, then you will get the result as 0. I hope you can see it. Let's say I have chosen A11, A21, A31. This is the first column. And I multiplied with C13, C23, C33. The cofactors of third column, C13, C23 and C33. So again, elements of the first column, but cofactors of the third column. You take their sum and product, it will again be 0. So did you get that part, students? I hope it is understandable. It is very well understood by all of you. That remains simple. Elements along with their corresponding cofactors give you the value of the determinant. But elements with some other row, let's say I'm choosing the elements of a row, then if I choose the cofactors of some other row, or if I'm choosing the elements of a column and I choose the elements cofactors of some other column and their product, then their sum, then it will become 0. I hope you will remember this as a fact. Now, the next part is even interesting. The next part is even more interesting. Now, what is this result I'm talking about? Let's say if I have a matrix, or let's say determinant as of now. So let's say we have a determinant here. That determinant is delta. It has its own elements A11, A12, A13. Then A21, A22, A23. Then you have A31, A32 and A33. I hope we can see it that this is a 3 by 3 determinant. So order is n. Order is 3, I'm really sorry. So let's say I write the determinant of its cofactor elements. So let's say A11 has a cofactor C11, then A12 has C12, A13 has C13, then C21, C22, C23, then you have C31, C32 and C33. Now what is this determinant? This is a determinant which is the determinant of the cofactors of these elements of the determinant delta. So delta was the determinant and I have taken the cofactors of all of these elements here, which is delta C. I am saying it delta C, which is the determinant of the cofactors of these elements. Now, can you relate it? The proof I'll discuss later when we discuss the properties, but at this stage, I'm trying to make you understand that this determinant and this determinant, their values have a relation. What is that relation? That relation I am bringing into picture here by introducing this, that if here, this determinant has a value delta, if this determinant has a value delta, you raise it to the power order minus 1. The order is 3 here, the order is 3 here, so 3 minus 1, that is delta square. That delta square will be the value of this determinant formed by the cofactors of the elements. Are you getting my part very clearly, students? Let's say if there was a 2 by 2 determinant, let's say A, B, C and D, right? And their cofactors, this is, let's say, is a determinant denoted by delta. And there is again another determinant which is, let's say, delta C, formed by the cofactors of A, B, C and D. Let's say that is C of A, C of B, cofactor of C and cofactor of D. So this determinant is the cofactor determinant of these elements. So this here is the cofactor of A, cofactor of B, cofactor of C and cofactor of D. Now, if I am taking the determinant here, if I am finding the value of this determinant, which is what? Which is delta C. So as per the definition, this delta C will be equal to, this determinant only raised to the power. What is the order here? The order here is 2 minus 1. N minus 1, the order n minus 1. So 2 minus 1 is 1. So in the case of a 2 by 2 determinant, the value of the determinant and the value of the determinant formed by its cofactors will remain same. But when it comes to a 3 by 3, then the value of the determinant formed by the cofactors will be the square of the original determinant. I hope that's exactly what I'm trying to make you understand here by having this part being discussed here. For a third degree determinant, third order determinant, it will be equal to delta square, but for a second order determinant, it will be equal to delta only. This is exactly what we have discussed so far. I hope there is no confusion on that. So let us move to the next question. What does it say? The next question is a question asked by JEE Mains in 2024. And let's see what does it say. It says alpha and beta are not equal to 0. Okay, their product is not equal to 0. We are given a determinant A. We are given another determinant B. Okay. We are told that this determinant B, let's say for a matrix for a while, because matrix and determinants have almost the same thing. But let's say for a while, let's call it a matrix. You will understand it later when we study the chapter matrix, that calling it a matrix here is not going to create a problem. So this matrix B, which is for us as of now is a determinant. So this matrix B is the cofactors of the elements of A. That's the best part. So this is the cofactor of this A. Okay. And then what are we asked? We are told the value of determinant AB is needed to be found. First of all, there is something which you are not aware of right now. So let's say I am asked to find the value of determinant AB. Well, that can be written as the product of determinant A and determinant B. So always remember that if I'm asked the value of determinant of A into B, I can write it as determinant of A into determinant of B. It means that if I am told determinant of A into determinant of B, I have taken it as determinant of, if I'm asked to write the determinant of AB, then I can write it as determinant of A times determinant of B, right? Now let's go back to this part. One more thing I know for sure is that this B is the cofactor of A. I hope you can see that it is the cofactors of elements of A. So if this B is the cofactors of elements of A, you know one more property. What I'm trying to make you understand here is another thing, that what is matrix or determinant B? Well, B is the cofactors of A. Now, what does it mean? It means if I am wanting to find the value of determinant of B, can I not say it will be equal to determinant of A raised to the power degree minus 1? So the order minus 1. So the order of determinant A is 3. So 3 minus 1 is 2. So determinant of B is nothing but determinant of B is determinant of A square. What does it mean when somebody asks you value of the determinant AB, which is determinant A into determinant of B, where if I know the value of determinant B, which is determinant of A square, so I'll be writing it as A square into determinant of A, which is determinant of A cube. So my question boils down to finding the determinant of A and cubing it. But the problem here is finding the determinant of A is not an easy task because A is given in terms of alpha and beta. So I need to ensure that this does not happen. I need to first of all find the value of alpha and beta, right? So how do I do that? I have this clue that this matrix B over here is the cofactor of A. So can I use or can I find cofactor of A and compare it with B? Because what is B? Cofactor of A. So we have A, and as per our knowledge, we can find the cofactor of A. And then we can compare both of them. That's exactly what I'll do. So let us find cofactor of A. So now I am going to find cofactor of A. Let us find that. Right. Now how do we do that? Let us simply start finding it. So I'll write the minors of the elements of A with the sign scheme. So if I write minors with sign scheme, I'll get the cofactors. We have already understood this part. So let us start writing the cofactors of A. Well, with this example, you'll get more clarity that how do you write the cofactors. So pay a lot of attention. I'll be doing a lot of calculation. Pay a lot of attention. A lot of things will happen right now. So here, I'll start with this cofactor of A. First of all, let's write the cofactor of beta. So here, the sign scheme first let's introduce. It will be plus minus plus, minus plus minus, plus minus plus. So plus will keep it plus, which means positive. I need not write it. So let's bother about the negative signs. So plus, then I'll have a minus sign here, then plus, then I'll have a minus sign here, then plus, then I'll have a minus sign here, then plus, then I'll have a minus sign here, then plus. So positive signs I'm not writing because they don't make any difference. They'll keep it positive only. But negative signs I'm writing explicitly so that I stay, worry free, that I need not worry about the sign now. All I need to write the minors, because with these signs, the minors will be cofactors. I hope you're getting this part very clearly. Now, how do I proceed with the next part? Let's find the minor of beta. The minor of beta will be, I hope you know how do we find the minor of beta. The minor of beta will be, remove this beta and this particular row in this column. You're left with these 4 entries. This into this minus this into this will give you the minor of beta. I hope you know this process now. So I'll straight away start doing it. Now pay attention to all the details very carefully. So minor of beta will be 2 alpha square minus alpha beta. I hope you can see this. What I'm doing here is 2 alpha square minus alpha beta. So that will be here 2 alpha square minus alpha beta, right? I hope there is no confusion on that. What about minor of alpha? So it will be remove this and remove this. So what are we left with? 2 alpha square plus beta square. Can you see that? So here it should be 2 alpha square plus beta square. I hope that is very well understood by you all. Then let's write the next entry. Next entry here is that I need to find the minor of this 3. Although I'm writing the cofactor, but with these signs, they'll get converted into the minor cofactors, right? So here it will be alpha square plus alpha beta. I hope you can see that, alpha square plus alpha beta. So this is alpha square plus alpha beta. Next, what do I have next? Next is finding this, right? So here, this and this are cancelled. What am I left with? 2 alpha square minus 3 alpha. Can you see that? So this is 2 alpha square minus 3 alpha. I hope no confusion on that. Then the next part, right? Plus minus plus minus plus. So this minus is for this particular part. Now, what am I supposed to find? The cofactor of this alpha, right? So this and this are removed. So 2 alpha beta plus 3 beta. So this should be 2 alpha beta plus 3 beta. So I hope you're understanding how are we finding the cofactors. Similarly, if I find this beta's cofactors, it will be this, which is alpha beta plus alpha beta, which is 2 alpha beta, but with a negative sign. So it should be minus 2 alpha beta. Well, then again, when I proceed further, plus minus plus, minus plus minus, so plus minus plus, so minus should be here with this entry. Now, when it comes to this, here and here, I'm cancelling this alpha beta minus 3 alpha, right? So this should be alpha beta minus 3 alpha. That is what I have gotten. That's brilliant. Now, let's talk about this part. This and this are cancelled. So beta square minus 3 alpha. Okay, so this is negative of beta square minus 3 alpha. I hope you are getting it very clearly. Now let's come to the final part. This and this are cancelled. So alpha beta minus alpha square. I hope you are going great. So alpha beta minus alpha square. That is what, as per our knowledge, would be the cofactor of A. But as per them, the cofactor of A is matrix B. So the corresponding entries should be same. If this and this are same, their corresponding elements should be same. That is what equality of matrices say. That if two matrices are same, their order should be same. And along with that, their corresponding elements should be same. Which means these entries should be equal to these entries. So I'll choose some entries wisely so that I'll have to do less amount of calculations. So here, if I start paying attention to these things, let's say I go to this part. Alpha beta minus 3 alpha and minus 2 alpha. Those two entries are same, positioned same. Third row, first column, third row, first column. So they should be same because these two matrices are equal, because this is cofactor of A, but according to them, this is the cofactor of A. So these two entries should be same. Which two entries I'm talking about, students? Which two entries I'm talking about? These two entries, right? So here, let's equate them. Alpha beta minus 3 alpha. I'm putting a separator here. So alpha beta minus, I am having 3 alpha here, is equal to minus 2 alpha, right? So if I bring this 2 alpha on the left hand side, I'll have this alpha beta minus alpha is equal to 0. If I take alpha common, it will be beta minus 1 is equals to 0. Do you all see that alpha cannot be 0? Because if alpha becomes 0, alpha beta will be 0, which is not true. We are already given this. So in that case, alpha cannot be 0. So here, I can conclude that beta will be 1. That's why we did all this. Once you have concluded beta to be 1, you use any other result and find the value of alpha as well. Because to find the determinant of A, I need alpha and beta both. Right? So let us find alpha. So to have alpha, which result can be used? You can use any result basically, but let me just find which can be used. So let's use any result, right? So whichever you wish to use, let's say this one I'm using, right? Beta square minus 3 alpha is equal to 5. Okay, so this one I'm using here. I hope no confusions on that. So here, negative of beta square minus 3 alpha. Third row, second column is 5, right? What is the value of beta? We have already cracked the value of beta, which is 1. I'll put it here. So if I replace beta by 1, this is 1 minus 3 alpha, but negative of this is needed to be taken. So 1 minus 3 alpha, negative will be 3 alpha minus 1. And here it is 5. So from here, 1 goes to the other side, 6 by 3, that is 2. So the value of alpha is turned out to be 2. So we have cracked the values of alpha and beta. I hope you have understood this part, that how did we do it. If I have alpha and beta with me, can I now find the value of determinant of A? Yes, we can. So that's your determinant A. Let's find the value of determinant A here. So determinant A will be, let's put these values, beta alpha 3. So beta alpha 3. So that is 1, 2, 3. So first row will have the entries 1, 2 and 3. What about the next row? Next row is alpha alpha beta, which is 2, 2, 1. So the next row should have 2, 2, 1. What about the third row, students? Minus beta alpha 2 alpha, which is minus 1, 2 and 4. So minus 1, 2 and 4. That is what you need to find out. The determinant of A is what I need to work upon now. Sarrus rule I think we'll like to use, because we know that determinants can be expanded along with any row or any column, but Sarrus rule is also there. So let's utilize that result. Let's capitalize that. So I'll repeat the first two rows, which will be 1, 2, 3, and then we have 2, 2, 1. Then I hope you know what is needed to be done. Principal diagonal. So 1 into 2 into 4, that is clearly 8, right? Then 2 into 2 into 3. So 3 into 2, 6. 6 into 2 is 12. So that's 12. Then 1 into 2 into minus 1, that's minus 2. So that's the product and the sum. Then minus 1 into 2 into 3, that is, I think, minus 6, I believe. Yes. Then 1 into 2 into 1, that is again plus 2 as per my knowledge. Yes. Then 2 into 2 into 4, 4 into 4 is 16. So that should be the value of this determinant A. I hope you have understood whatever I have done so far. All I have done is 1 into 2 into 4 plus 2 into 2 into 3 plus minus 1 into 2 into 1. This is what I have written over here. Then minus 1 into 2 into 3, 1 into 2 into 1, 2 into 2 into 4. That sum I have written over here. So that is going to be the value of the determinant. Now that value is going to be, I think, 12 plus 8 is basically 20. 20 minus 2 is 18, right? 20 minus 2, yes, that is 18. Minus here 16 minus 2 is clearly 10. 10 plus 2 is 12. So 18 minus 12 is 6. So determinant of A is found to be 6. But what were we asked? We were asked the cube of determinant of A, which is 216, which I think you all are capable of writing or marking. The option B is supposed to be marked. Question was a little lengthy because cofactor was a very crucial role which was needed to be played. But I hope rest of the question made complete sense that this part is also very crucial where we used this particular property that I'm talking about, this particular property. So if you know the basics, if you know the concepts, if you know the properties, the question, the solution, the calculation becomes a little easier. And that is what you need to take care of. With that, let us proceed further and let us see what unfolds next. Now, after getting clarity on this particular question, let us see what comes next, what gets unfolded. Well, what you need to understand is that students keep on asking that, sir, what are the applications of determinants? Why are we discussing all this? So after understanding this much part, that what are determinants, how do you expand them, what are minor and cofactors, now you will start understanding that here are the applications, a wide range of their utilities in JEE mathematics. A lot of things are there, we'll unfold them one after another. So in every single chapter, there could be some use of determinants, and that's exactly what will start unfolding now at this particular stage. First of all, let us understand how do you use determinants in coordinate geometry. So let's say if I'm giving you a triangle, let's say if I were to give you basically a triangle, let's say a triangle looks somewhat like this. Any triangle, any kind of triangle, it could be scalene, isosceles, right angle, any sort of triangle it can be. That's the advantage. See, when you study up till 9th and 10th standard, the geometry said that you need to remember different formulae for different types of triangle. For equilateral, you had a different formula. For right angle, for isosceles. So these kinds of different formulae, Heron formula, a lot of formulae you had to learn. But here, when it comes to deal with coordinate geometry, it simplifies a lot of things into one single thing. That's exactly what we are trying to make you understand. That let's say if you are given a triangle where its vertices are x1 comma y1, second vertex could be x2 comma y2, and the third vertex could be x3 comma y3. Let's say these vertices are denoted by A, B and C. And if I were to ask you to find the area of this triangle, the formula remains very simple. With the help of determinants, all you need to do is a very simple expression, students. This area, which we are denoting by delta right now, is half of. But of course, you need to put a modular sign here because this determinant may give you either a positive value or a negative value, or even 0 if the points are collinear. But if it is negative, in that case I need to ensure that the area should always be a positive quantity, hence I'll put a mod over it. So 1 by 2 will remain as it is. You will find the value of this determinant which says x1 y1 1, x2 y2 1, x3 y3 1. But here modulus also comes into picture, that whatever value it generates, you're supposed to put a mod sign over here, and that's how you find the area of a triangle. Let me tell you one more secret. You need not even do this. There is one more even better method of finding the area of any polygon. So polygon means triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, any sort of polygon if you are dealing with, you can very easily find the area of any triangle by using another method which we call as the stair method. Let's learn that method. Now that's something very interesting, students. If you remember it, it will help you a lot in applying this particular learning in your JEE journey. So let's say we are asking you to apply this stair method to find the area of any polygon. So area of any polygon can be worked out. For example, let's say you are having a quadrilateral, right? So let's say this is a quadrilateral, any kind of quadrilateral it can be, regular, irregular, square, parallelogram, rhombus, kite, any kind of a four-sided closed shape you're dealing with, basically in a simpler language. Or even if it is a rectangle or even a quadrilateral, pentagon, hexagon, heptagon, this single formula which I'm sharing in the context of this quadrilateral is applicable on all sorts of polygon. So let's learn that formula. This is called stair method, first of all, which is a very simple method, which is a very efficient method in finding the area of any polygon. For example, we are given a polygon which has the vertices A, B, C and D. Let's say A has the coordinates x1, y1, B has the coordinates x2, y2, C has the coordinates x3, y3 and D has the coordinates x4, y4. These are the four vertices. One thing you need to ensure is that when you apply this stair method, you move either in the cyclic manner, that means clockwise or anti-clockwise. You cannot jump abruptly to any vertex. For example, if I start choosing these points, when I start applying these points into my formula, the formula I'm going to give you right now, then either you will go clockwise. So whichever vertex you wish to begin with, you can begin with any vertex, whichever you wish to. Let's say you want to begin with the vertex A, then from A you go to B, then C, then D. So that's how you have been moving in a clockwise manner. No sir, we don't want to do that. Perfectly fine. Let's say you want to begin with B. Yes, you can begin with B. And let's say you don't want to go clockwise, you wish to go anti-clockwise. That is also fine. So you start with B, then A, then D, then C. But what you cannot do is that let's say from B you jump to D, then C, then A. No, that's not something which you can do. Remember, so use this cyclicity, either go clockwise or anti-clockwise, but you cannot jump abruptly. Now, the order, if understood by everyone, let's learn the formula. The formula is even simpler. The stair method says that the area of this quadrilateral ABCD is given by half of mod of stair of. Now what is a stair? Let me write it first, then I'll explain this particular part. Stair of whichever vertex you wish to begin with. Let's say I'm willing to begin with x1, y1. So I'll write this x1, y1 first. Then I'll write the next vertex x2, y2. Then I'll write the next vertex x3, y3. I'm moving in the clockwise direction. And then I move to the next vertex x4, y4. Now you're supposed to write that same vertex again with the vertex you begin with. So I begin with the vertex x1, y1. So I need to rewrite this particular vertex again x1, y1. I'll take the stair of it and then I'll take the mod of it. Sir, you're constantly mentioning stair of it, stair of it, stair of it. What does stair of it means? A very simple concept. It is, the students. We'll do a cross multiplication now. But from left to right, we'll take it positively, and from right to left, we'll take it negatively. Sir, what are you saying? We are not able to digest anything at all. We are getting confused. I think that method through determinant was even simpler. Trust me, this is even simpler. This is the simplest one actually. How? Let me explain that part. So what I'll do is, I'll first of all multiply x1 with y2 minus x2 y1. Then plus x2 y3 minus x3 y2 plus x3 y4 minus x4 y3 plus x4 y1 minus x1 y4. Did you realize the ease with which you can approach the area-based questions of any polygon? What I'm saying here is a very simple concept, students, that this area is half of modulus of stair of. Now what does it mean? I'll rewrite this part, half of modulus of. Now this particular part, right? What did I do? I begin with x1, y2. So I need to write x1, y2 minus x2, y1, right? Plus x2, y3 minus x3, y2. I hope you are comfortably understanding this. Then x3, y4 minus you have x4, y3, which I'm writing here. Then you have x4, y1, then minus x1, y4. I hope this makes complete sense and you are able to understand this particular formula very clearly. But this expression may be either negative or positive or zero. What you need to understand is if it is zero, the points will be collinear because there is no shape getting created, which means the area should be zero. Or if it is not zero, then it could be either positive or negative. Well, negative does not signify anything here. All you need to do is take the modulus of it so that the area always remains positive. So half of mod of stair. Now this stair formula can be applied on triangles as well. And if it can be applied on the triangles as well, I think then rather than using this determinant formula, you have an even simpler formula, which is half of stair of x1, y1, x2, y2, x3, y3, x1, y1. And I hope now you know how to expand a stair. Did you get that part? I hope it makes complete sense. And if this particular part is understood by you all, let us proceed further and let's delve a little more deeper with this particular explanation that if the area is found to be zero, if we are given a triangle, x1, y1, x2, y2, x3, y3 are the vertices of the triangle, and by using this either determinant method or stair method, if I find that the area of the triangle is zero, well, when does that happen? Sir, area of the triangle will be zero if all the 3 points are collinear. If they lie on a single straight line, then we don't think that any triangle will get formed. Basically, in that case, what will happen? That no triangle will be formed, and such triangle, which is not a triangle at all, will have the area zero. Since no triangle is formed, its area will be zero. Which means if I apply either this determinant on x1, y1, x2, y2 and x3, y3 in this manner, or if I take the stair of it, if it is found to be zero, then we can claim that these 3 points or 4 points, or no matter what number of points we are given, that this area should be zero in that case. Always remember, in the case of triangle, whether you move anti-clockwise or clockwise, there is no chance that you jump from here to there. But when the quadrilateral pentagon comes into picture, you need to ensure that you are maintaining either a clockwise order or an anti-clockwise manner. So that is what you need to follow or abide by. Now, let us look at the next application of this thing, determinants, into coordinate geometry. Well, this is something which I don't recommend you to learn or memorize at this stage at all. What I'm trying to tell you is, let's say if you are given 3 straight lines. Let's say if you are given 3 straight lines, first, second and third. So if I'm given 3 straight lines, of course, their equations may look like a1x plus b1y plus c1 is equal to 0. This equation may have the equation a2x plus b2y plus c2 is equal to 0. This line may have the equation a3x plus b3y plus c3 is equal to 0. Now, if I were to ask you, can you help me in finding the area of the triangle formed with the help of these 3 straight lines? Can you do that? The approach will remain very simple, students. Either you use this formula, which looks very difficult, and indeed it is very difficult, or rather I suggest you a more simpler method. Do you know how to solve linear equations in 2 variables? So, I hope you understand. If I solve this equation and this equation, I can find the point of intersection of these 2 lines, which will be this vertex, which we can find quite easily. If I solve this equation with this equation, I'll be able to find this vertex. And if I solve this equation and this equation, I'll be able to find this vertex as well. And once you have found all the 3 vertices, you will get the area of the triangle. So this looks too heavy in terms of efforts. If effort wise it is seen, this is too heavy. Solving pairwise two equations, thrice, and then you find the vertices and then you apply the area formula, that will be, tough or lengthy in terms of calculation. Tough, I won't say, but lengthy, yes. But trust me, even if you apply this formula, this is also asking you the same amount of calculation. How? Let's have a look at that. See, I am given three straight lines. A1x plus B1y plus C1, A2x plus B2y plus C2, A3x plus B3y plus C3 is equal to 0, right? Now, these are the three sides of a triangle, and there is a formula through which you can directly find the area of the triangle. But trust me, it is not that easy. Why? Let's look at that. First of all, of course, you will find the determinant A1, B1, C1, A2, B2, C2, A3, B3, C3, and you will square it. Okay, that is perfectly doable. We have the equations. We have the three lines A1, B1, C1, A2, B2, C2, A3, B3, C3. By using the Sarrus rule, we can expand it and we can find the determinant and then we can square it. But with this, you need to multiply something else as well. Now, what is that? Half of mod of C1, C2, C3. Now, this C1, C2, C3 is not this C1, C2, C3. This C1, C2, C3 were the smaller C1, C2, C3. What is capital C1, capital C2, capital C3? Well, capital C1, capital C2, capital C3 are the cofactors of the elements C1, C2 and C3. Did you get my point? What I'm trying to make you understand is, if I ask you what is capital C1, what is capital C1? Well, here in this case, capital C1 will be cofactor of small c1. And cofactor of small c1, I hope, is going to be very well understood by you all if you know this very basic concept that cofactor of small c1. This is capital C1 I'm writing over here, right, students? So this should be A2B3 minus A3B2. So this is the determinant of A2B2 and then A3B3, and this I think is the minor. I haven't mentioned the sign as of now. Sign scheme, as per the sign scheme, plus minus plus. So before here a plus sign should be there, which is already there. So this is the cofactor of small c1, which is capital C1. Similarly, I will find capital C2, then capital C3, I think, which you all are able of doing. Then after finding capital C1, capital C2, capital C3, you multiply all of them and then you get the result or the area of the triangle, which I hope you're realizing is again a cumbersome process. So yes, calculation is going to be there. Either you use this formula or use this logical method. Now, why am I emphasizing you to not use the formula and apply this logical method? Because formula, remembering the formula is again a tedious task. So why not simply remember the logic, apply it and get the answer? Because this is something which you are aware of, which you already know, rather than learning a new formula, which is also very tricky, which is also very confusing. And if you commit any error, you will get the wrong answer. And wrong answers are always given in the options. Do you know that? They always ensure that whatever error you will commit and whatever wrong answer you may get, that answer possibly is given in the options, and you very confidently mark that wrong option, with a lot of confidence that yes, I have marked it correctly, and you go ahead with the next question. Well, that's a problem. That yes, whenever confusion arises, try to simplify this. Keep your approach simpler, because genius is keeping complex things easy, not easy things complicated. Remember that. Now, let us proceed further. Let us learn more applications of determinants in coordinate geometry. Again, I'll say very simply that if you have 2 points x1, y1 and x2, y2, what we have learned it that any line passing through these 2 points x1, y1 and x2, y2 will have the equation y minus y1 upon x minus x1 is equal to y2 minus y1 upon x2 minus x1, and this is exactly what we'll do. 2-point form of a straight line, right? This is what you study when we study coordinate geometry. But when it comes to finding the equation of a straight line through determinants, the formula remains very simple. You can apply the condition for collinearity. What do I mean by that? See, x1, y1, x2, y2 and that variable point x comma y, whose locus we are trying to find. These 3 points will be collinear. If these 3 points are collinear, then x, y, 1, x1, y1, 1, x2, y2, 1 will have the determinant 0. That can also be done. So this is also how you will get an equation in x and y, which will be a linear equation, and that will also represent the same straight line. So either you use this or this, you will get the same straight line. I hope you are getting this particular part. Well, Proceeding ahead, let us learn few more concepts. Another concept says that if three lines are concurrent, that's a very important result, and I will emphasize, strongly recommend that you should learn this. You should by heart this. Now, what is that result? What is that learning? Let's say you are given three straight lines. Two of them are these. Let's say this is your first straight line, L1 is equal to 0. This is your second straight line, L2 is equal to 0. Where L1 can be A1x plus B1y plus C1. L2 could be A2x plus B2y plus C2, right? So if I have these two straight lines and they are intersecting at a certain point, and there is another third straight line, let's say L3 is equal to 0, and luckily that straight line L3 also passes through that same point where L1 and L2 are intersecting. What does it mean, students? It means that L1, L2 and L3 are concurrent. What do I mean by concurrent? If I'm given certain number of lines and all of those lines are passing through one single common point. Let's say if I'm given a lot of lines are given to me like this. And what is special about all these lines? That all these lines are passing through one single point. That all these lines are intersecting at that one common point. Then I'll call this family of lines as concurrent lines. This family of lines is said to be concurrent lines. So in case if I'm asked to check or assess whether three given lines are concurrent or not. So one of the methods is, sir, solve L1 and L2, let's say for a while. You will find their point of intersection. And if that point of intersection satisfies the third line, which means all the three lines are passing through one single common point, and that's how you can claim that lines are concurrent. Sir, what if I don't want to use this particular version? I don't want to use this logical approach. Do we have something shorter? Do we have something simpler? Yes, we do have. A very straightforward formula, students. Remember this, that if you have three lines, A1x plus B1y plus C1 is equal to 0, A2x plus B2y plus C2 is equal to 0, and A3x plus B3y plus C3 is equal to 0. Take the determinant of the coefficients. So A1, B1, C1, A2, B2, C2, and A3, B3, C3. And if this determinant is found to be 0, if this determinant of the coefficient is found to be 0, you can say that these three lines are definitely going to be concurrent. Did you learn this result? Did you understand how crucial determinants are? What you need to understand is through logical approach you can find the solutions. But determinants are there as a tool, as a method, as an approach, and they make you more efficient and effective in terms of solving a problem. And this exam is all about getting the answers quickly, as quick as possible. And if you are given certain tools which will help you more in getting your answers more closely, more quickly, then why should you not have them? As we have already discussed a lot many times, that Abraham Lincoln has once said it, that if you have 6 hours to cut down a tree, spend the first 4 hours in sharpening the saw. So having this tool with your approach will actually sharpen your saw. You will be more efficient, you will be more effective. That's exactly what we are asking you to do. Well, there is one more very crucial application of it. What is that application, students? Let's say if I am given a second degree equation. If I am given a second degree equation, ax square plus 2hxy plus by square plus 2gx plus 2fy plus c is equal to 0. So if I am given this particular second degree equation, now please remember this second degree equation comes up with its own variants. It can represent a pair of straight lines, it can represent a circle, it can represent a parabola, it can represent an ellipse, or it may represent a hyperbola. So there are 5 possibilities this pair of straight lines may come up with. Although what will be represented, we don't know that much, but one conclusion for sure can be drawn at this stage. What we are discussing is that this straight line, which is a second degree equation in 2 variables, can represent either a pair of straight lines or a conic which includes circle, parabola, ellipse or hyperbola. So we'll talk about circle, parabola, ellipse and hyperbola later in coordinate geometry, but right now I am trying to give you the idea that this equation in second degree with 2 variables may represent a pair of straight lines. Now, when will it represent a pair of straight line? That is what we'll be discussing. How do I remember this as a formula? Please have a look at that. First of all, let's look at this coefficient of x square, coefficient of y square, and the constant term. We write these three things at the principal diagonal, A, B, C. Then look at the coefficient of xy, take the half of it. Coefficient of x, take the half of it. Coefficient of y, take the half of it. Which means three things I'll get, h, g, and f. All you need to do is write h, g, and f here like this, and symmetrically write h, g, and f like this. How do I remember it? I have discussed the technique. First of all, coefficient of x square, y square in the constant term will come at the principal diagonal. And then half of the coefficients of xy, x and y, which are h, g, f. Write them here and here symmetrically. And if this determinant is found to be 0, this here, the equation in second degree in two variables will represent a pair of straight lines. This means this equation contains two lines and this is the product of those two lines equations. I hope you are getting this language very clearly. For example, if I am given two straight lines somewhat like this, let's say a1x plus b1y plus c1 is equal to 0 and a2x plus b2y plus c2 is equal to 0. So these are the two straight lines. What I have first of all done is I have brought all the terms on the left hand side, and on the right hand side I have kept 0. First of all, that's the prerequisite here. And then if I multiply both the equations, so this equation's LHS is multiplied by this equation's LHS, and their RHS are also multiplied respectively. So here I'll get the product of this equation with this equation here, and when these two are multiplied, something of this sort gets generated. This equation represents a pair of straight lines if ABC, HGF, determinant represents or becomes 0. So what if it is not 0? If it is not 0, then it will represent a conic. Sir, which conic? Circle, parabola, ellipse or hyperbola? That let's keep for later. H square and AB are related, and some more things are there which we will discuss later, not at this stage. When we study coordinate geometry, circle, parabola, ellipse and hyperbola, at that stage I'll make you recall this formula and I'll tell you this is what we have discussed in determinants. Now let's discuss it in conic. We'll discuss this more meticulously later, but at this stage, remember, if you are given this particular equation, second degree equation in two variables, and you are asked to find whether it represents a pair of straight lines or not, you apply this determinant and check it. I am saying this, learn it. Remember it. There is no substitute of it. Learn it. This formula is needed to be remembered by you. So remember it, learn it, take notes of these formulae in your handbook where developing the short notes. There also you can write such short techniques which we are bringing by fetching a lot of books, a lot of sources and a lot of resources. Now let us proceed further. Now let us talk more about what else we have brought for you in this picture. Again, there comes another formula, a very important version, that if I'm given 3 points, let's say I'm given 3 non-collinear points, x1, y1, x2, y2 and x3, y3. So of course, if I'm given 3 non-collinear points, I can have a circle passing through these through non-collinear points. So let's say this is A, this is B and this is C. This here is C. And these are the points A. Let's say this is B and this here is, let's say, C. Now, if I'm asking you to write the equation of the circle which passes through these 3 non-collinear points, then you need to find this determinant's value and it will be the equation of the circle. I am again not asking you to do this. Solving a 4x4 determinant, first of all, is out of your syllabus. Second, even if it is, if it can be done, even if I teach you the expansion of a 4x4 determinant, then also it will be a very cumbersome, very huge practice, which we'll avoid. So in that case, what will we do? What should we do? Well, the approach remains very simple. Let's say I have given you 3 non-collinear points and I have asked you to write the equation of a circle. And how will you do it? That's the question. Trust me, by some means, if you're able to crack the center of this circle, if if there is any approach through which you could find the circle of this center, you will be able to write the equation of the circle with a lot of simple steps. How to find the center of the circle, sir? That is what we need to understand. Okay, let us work on finding the center of the circle. First of all, let's say I join this A with B, and then I join this C with B, and then I join this A with B here. Can I say I am getting a triangle over here? So can I say I am having a triangle ABC which has this circle circumscribing it? Okay, that's perfectly fine. Even if you don't create this triangle, we can understand this with a lot of ease. But this triangle I have drawn deliberately to make you understand that in case if you are given a triangle ABC whose vertices are given to you, x1, y1, x2, y2 and x3, y3. And if the equation of the triangle, if the equation of the circle which is circumscribing the triangle ABC is asked, then also the same approach is needed to be applied, which we'll be discussing right now. So I repeat, what I am suggesting you here to do is something very impressive, something very interesting, through which you will be able to solve two sorts of questions which require the same simple method. What kind of two questions? First question, if I give you 3 points ABC and if I ask you that these 3 points are non-collinear, find the equation of the circle passing through these 3 points. First category of questions. Second category of questions. Let's say I give you a triangle ABC and I ask you, write the equation of the circle circumscribing this triangle ABC. Well, in that case also, the same method needs to be applied. So you have been talking about the question. How to solve, please discuss that. That's exactly what we'll do now. How should we solve such category of questions? That's exactly what we'll discuss now. What did I mention in the beginning? You need to work on finding the center. Once you find the center, trust me, the job is done. How? Let's have a look at that. Sir, let's say this here is the center of this circle. This here is the center of the circle, which should also be said the circumcenter of the triangle ABC. I hope you are remembering it. You are able to recall something. So let's say this center here is P. Let's say this center here is P, which can be taken as either H comma K or alpha comma beta, whatever you wish to call it. So let's say P's coordinates I'm assuming to be alpha comma beta, right? So this is what I have assumed. Now what do we know? We know a very important thing which will solve your job, which will solve your entire question. What is that? That part is very simple, students here. That can I say this PA over here or PC over here or PB over here, all of them are the radii of this circle. If PA, PB, PC are the radii of the circle, can you not say that, sir, the job is done? How and why? Let me tell you, by using the coordinate geometry, you will say PA, PC and PB are equal. If PA, PB and PC are equal, which means distance wise, their squares will also be equal. So PA square will be equal to PB square will be equal to PC square. Now I hope you know how to use the distance formula. Let's say the coordinates of A are x1 comma y1. So what will be PA? PA will be under root over alpha minus x1 whole square plus beta minus y1 whole square. I hope you know this formula. So when you square it, even under roots are removed. So what will be the value of PA? PA will be x1 minus alpha whole square plus y1 minus beta whole square. What will be PB? PB will be x2 minus alpha whole square plus y2 minus beta whole square. What will be PC square? Well, PC square will be x3 minus alpha whole square plus y3 minus beta whole square. I hope I have written it correctly. Yes. Now what should we do, sir? It does not look very simple. Trust me, it is very simple. It is very simple. Now what you are supposed to do is take these two first, solve this and this first. You will see x1 square, you will see alpha square getting cancelled, beta square getting cancelled. A very simple linear equation will be found in alpha and beta. Similarly, solve these two, this equation and this equation. Again, alpha square, beta square will get cancelled by alpha square and beta square here, and you will get a very simple equation in alpha and beta. So again, I have gotten two equations in alpha and beta, which means two linear equations, two variable alpha and beta. By solving them, alpha and beta can be found. By solving them, alpha and beta can be found. And once you have found alpha and beta, you got the center of the circle. You got the center of the circle. And by putting alpha and beta either here or here or here, you can find the radius of the circle, because PA square, PB square and PC square are the square of the radii. So I will have the radius of the circle. I will have the center of the circle. So once you have cracked the radius of the circle and the center of the circle, is it really a tough task for you to write the equation of the circle? I hope you know that if I were to give you a circle which has a center, let's say alpha comma beta. Let's say I'm giving you a circle which has the center alpha comma beta and it has the radius r. Will you not be able to write its equation? Its equation to you should be x minus alpha whole square plus y minus beta whole square is equal to r square, and the job is done. Well, that helps you in decoding another category of questions when, if I had asked you that there is a triangle ABC is given to you, find its circumcenter. Such questions are asked in coordinate geometry. So if you are asked to find its circumcenter, how will you do it? We are telling you the modus operandi, the SOP. So I am constantly telling you that this formula is completely useless. Apply logic. Even if you say that, no sir, I will memorize this formula and I wish to use it, I have given you complete liberty to use it. But trust me, eventually you will realize that this method is less time consuming. This is more efficient. This is not very effective method as far as determinants are considered in this particular case. So I'm giving you the complete approach. I'm giving you both the tools. Now I'm giving you the liberty that whatever you wish to use as per your intelligence. But I'm telling you the pros and cons, that how will something will assist you more effectively. Did you get that part, students? So I think a lot of clarity is received by you as far as this particular part is considered. Well, JEE Mains in 2021 has asked you a question. Let's look at this question and understand how to solve it. So we are told A, B and C. There are 3 points. We are also told that B is not equal to 0 and mod B is not equal to 1. Okay, we'll use it later. But then we are told that these are the 3 points such that the area of the triangle ABC is 1 square unit. Okay, 1 square unit is the area of the triangle ABC. Now, it says sum of all possible values of A is. JEE Mains in 2021 has asked us. So let us work on finding the area of the triangle and then we'll do something. That's what we know. That's what we do. Yes, that's what we'll do. So how should we proceed with this question? That's what the mindset which is required here in this particular question. I hope you know you can use either determinants or stair method to find the area of a triangle. So can we use the stair method to find the area of the triangle? How? Let's have a look at that. So what did stair method say? Stair method said that area of a triangle will be half of mod of stair of these 3 vertices. Which 3 vertices? A comma 0, then B comma 2B plus 1, then 0 comma B, and then A comma 0, because whichever vertex you begin with, you're supposed to end it with the same vertex when you apply the stair. Now, this area here is given to be 1. So we are already told that this area should be 1, right? So I'll use this particular part later, that this area is 1. First of all, let me simplify this particular stair over here. So this stair over here turns out to be half of mod of what? Mod of A into 2B plus 1. Well, that will be 2AB plus, I think, A. I hope we are going great. Now, minus B into 0. So that will be 0. I need not write it. Plus B square. So that is what I'll write now. Minus 0 into 2B plus 1, which will be 0. I need not write it. Plus 0 minus AB. So I'll write another minus AB here. And I'm supposed to take modulus of it, right? So that's the area of the triangle as per our understanding. But as per their understanding, the area of the triangle is given to be 1. The area of the triangle, what they have given is 1. This 1 is the area of the triangle ABC. That is what they have given in the question, right? So I'm writing it here so that you understand it more clearly. Now, What should I do? I'll take this 2 on the other side. It will become 1. I hope you're getting it. This is what we were given. This area was given to be 1. So I'm solving this equation here. 2 I'm taking on the other side, so it becomes 2. Then I'll remove this modulus sign. So when you remove the modulus sign from an equation, you're supposed to use plus minus sign. Either you square both these sides or you use the plus minus sign. I think squaring will make it more difficult. I'll use the plus minus sign. So if I'm removing mod here, I am left with a plus b square. Then 2ab minus ab is plus ab. And there you have 2 into 1, 2, but you're removing mod, so you're supposed to use a plus minus. So plus minus 2 is what you're supposed to do. I hope this part makes complete sense. Now, what are we asked? We are asked the values of a, right? We need to deal with the values of a. So let us start working on finding the values of a, right? So from here, if I keep a plus ab, a plus ab here, and if I take this b square on the other side, I have plus minus 2 minus b square. And if I take a common from here, then I'll be left with b plus 1 here. And on the other side, I hope I'm going great, a times b plus 1. And there you have plus minus 2 minus b square, plus minus 2 minus b square. Yes, that's great. So from here, I'll get this value of a, which will be plus minus 2 minus b square upon b plus 1. So this is the value of a, but rather I should say these are the values of a, because I'll use plus 2 once and then I'll use minus 2. So I'll be getting two values of a. What are these two values of a? One of the values will be plus 2 minus b square upon b plus 1, and the other value will be minus 2 minus b square upon b plus 1. What were we asked in the question? We were asked to find the sum of all possible values of a. I think as per our understanding, we could find two values of a. And what are we supposed to do? Take the sum of these two values. So I'll add these two values. What are we asked? Sum of all possible values of a, which should be this. I hope there is no confusion on it. So if I take the LCM is b plus 1, b plus 1. So that is what will be there in the denominator. So b plus 1 is there in the denominator. What will be there in the numerator? So 2 minus 2 will be 0. Minus b square will be minus 2b square. So minus 2b square upon b plus 1 should be our answer, which is given in the option D. Was it a simple question? Was it an easy question? These questions will look very simple, very easy only when you know these concepts. Which concepts? Area of the triangle, modulus, how to deal with the modulus sign, and how should you interpret the question, understanding the language. If all these things are done with utmost sincerity, focus and attention, you will get your results. Approach remains very simple. Stay cautious, read the question with all the focus you have, stay attentive, stay alert, and if you are in the moment, you will get the answer. Don't worry about the past or the future. Stay focused in the present. That's the key in getting the answers to questions of this particular category which are asked by JEE Mains and Advanced. Well, if this particular question is understood by you all, let us proceed further towards the next category where we study useful operations. So now we are moving towards the part where we'll be discussing some very crucial operations. Well, these operations are not just simple operations. These are the operations which will help you in expanding or finding the value of a determinant very easily. A lot of times what you see is that you need to solve a determinant. But if you pay some attention, if you be a little more observant, and if you apply some basic observations on your determinant, then you will be able to solve that determinant more effectively if you know certain properties. So there are a lot of properties through which you can actually find the value of the determinant very easily. But to know those properties, you should understand some useful operations. Now, let's understand those useful operations first, and then we'll understand those properties, and then we'll learn how can these determinants be expanded with more ease, with more simplicity. Let's have a look at that. Let's understand some operations. For example, if I want to interchange any row with another row or a column with another column. For example, if a determinant has second row and third row, and if I want to interchange them, So I can write it like this, that row 2 is being interchanged by row 3, and this is how you write this bidirectional arrow. Or let's say if I want to change column 1 by column 2, interchange column 1 by column 2, this is how I'll write it. So interchanging a row with another row or a column with another column is written like this. Well, similarly, there is another set of operation exists. What is that operation? The addition of m times the elements of jth row to the corresponding elements of ith row is denoted by, for example, let's say there is a row, let's say there is a second row, right? And to the second row, let's say I'm multiplying it by 3. And let's say I am willing to add it to another row, let's say row 3. So what I've done is I have here added something, multiplied something to row 2, and then I have added it with the another row, row 3, and I'm making this amendment, I am making this update in the third row. That's what I'm doing here. So can that be done first of all? Yes, this can be done. But when this is done, what happens? How do you deal with them? That part we'll discuss later. But first of all, I'm making you understand that how do you interpret these operations. So operation here is very simple. The operation says if I'm multiplying a certain row by a certain number, and if I'm adding with a certain row, and then I'm updating this particular result into some other row, then this can be done. Well, the same operation can be done column wise as well. Let's say if there is a column, let's say column 2, column 3, let's say, and on column 3, I want to make some amendment, let's say, column 3 minus 2 times column 1. So what I have done here is, I have multiplied all the values of column 1 by a certain value, and then this expression I'm adding to column 3, and whatever result I'm getting here, I'm updating that result in the column 3. Such operations are called these, row-wise or column-wise operations. Not just that, but this can be stretched up to a better extent. What is that? Let's read it first, then you'll understand it more clearly. What do I mean by this particular part? The addition of m times the element of jth row, and n times of the element of the kth row to the corresponding element of ith row, denoted by Ri is equal to Ri plus mrj plus nrk. What does it mean? It simply means, students, that if let's say I want to update row 1, I wish to update, this is what I'm removing first. Let's say I wish to update row 1, but again I wish to make some amendments in row 1. How? Let's have a look at that. In row 1, I wish to have row 1, then I wish to have double of row 2, but I wish to subtract triple of row 3. So this is another operation which you can perform, and I'm just explaining that how do you write these operations, how do you understand these operations. What does this operation mean? That in row 1, you make an amendment. Now what is that amendment? That you will have row 1's element plus double of second row's element minus triple of row 3's element. If this operation is done on row 1 plus 2 row of row 2 minus 3 times of row 3, then this expression, whatever value it yields, that value is substituted or replaced in row 1. So such operations are being done, and this same operation in the same manner can be done column wise as well. For example, if I wish to write, let's say if I wish to make some change on column 2, well, how can that be done? So let's say if I wish to make some change on column 2. So on column 2, let's say I wish to write, let's say column 2 plus let's say 2 times column 3 minus column 1. So this is how I can make such corrections or amendments column wise as well. So these are some useful operations which we'll do. First was interchanging a row by a column, and second and third can be understood in a clubbed manner, that updating any row or any column by applying such category of operations that can be done. How to do it? What does it have any effect on the determinant? All that part we'll discuss later when we start discussing properties of determinants. But I hope this part here does not make any confusion at all. Now let us look at this, that with the help of those useful operations, what properties can be observed and understood as far as a determinant is considered. Let us understand the first property here. What does the first property says? First property says that the value of the determinant, remains unaltered, unchanged, intact when rows are changed into corresponding columns. When we discuss matrices, there will be discussing the transpose of a matrix. Transpose of a matrix means interchanging rows by columns. So if I'm dealing with a square matrix, what does a square matrix mean, students? Square matrix means the number of rows and number of columns are going to be same. That's exactly what determinants are. So if number of rows and number of columns are same, that is what square matrix is. So if you are taking the transpose of a square matrix, now, what is the meaning of transpose of a square matrix? Transpose of a square matrix means that you are interchanging rows by columns. For example, I'll just make you understand it with more clarity here. Let's say there is this determinant A, which is, let's say, A, B, C, and D. And I have interchanged its rows by columns and vice versa, rows by columns or columns by rows, which means if I am writing its transpose, then it will be AB being the first row will become the first column, CD being the second row will become the second column. Trust me, whether you find the determinant by using this method, AD minus BC, I hope you can see the determinant A here is AD minus BC. Or if you find the determinant here, it will also remain same, AD minus BC. So what I am trying to make you understand is that whenever you deal with the determinant, interchanging its rows by its columns won't change its values. Second learning. When it comes to matrices, the same phenomena, the same process is called taking the transpose of a matrix. So if you are dealing with a square matrix, which has the same number of rows and columns, and if you take its transpose, then both of the matrices, the original matrix and the transpose of the matrix, will have the same determinant. Where did it come from? Here. So I hope you'll remember the first property, that if you have this particular determinant, or if you take its transpose means basically interchanging rows by columns, then also it will generate the same values. I hope this property is very well understood by you all. You will remember it. I hope we can proceed further now. Now, let's look at the next part. What is the next part here, students? Second property. What does the second property say? It says if any two rows or two columns of a determinant are interchanged. If any two row or two column are interchanged, then the sign of the determinant is changed and the numerical value remains unaltered, unchanged, intact. It does not change. What does it mean? It simply means, please understand students, let's say if you are having a determinant here 2, 3, minus 1 and 5. Let's say this is the determinant, right? So you had this determinant, I'll rewrite it 2, 3, minus 1 and 5. This here is the determinant, right? Now in this determinant, let's say I have performed an operation. Let's say this is a determinant A. I am performing an operation that I am either interchanging first row by second row or first column by second column. That's all what I can do here because this is a 2 by 2 determinant. So let's say I have made a change. What change I am making here? I am interchanging first row by second row. I hope you must have remembered this operation. So when you are interchanging first row by second row, what happens here is that here first row by second row. So it will become minus 1 and 5 and this will become 2 and 3. So what did I say here? Let us find the value of this determinant here. Well, it should be 2 into 5. This is 10 and minus 1 into 3 is minus 3. Minus of minus 3 is 3, which is 13. What about this determinant's value? I hope you can see the value of the determinant here will be minus 3 and then this will become minus 10, which makes it minus 13. Did you get this? Minus 13. What does minus 13 means? Minus 13 means negative of determinant of A. That's exactly what I was trying to make you understand here. So if you are interchanging any row by any column, I'm really sorry. If you're interchanging any two rows by themselves, row by row, or a column by a column, then the value, numerical value of the determinant does not change, but its sign changes. Its sign changes. I hope you will remember it. Sir, can I apply multiple such interchanges? Which means, let's say here I'm applying two operations. Which two operations? Let's say first I'm interchanging column 1 by column 3 and then column 2 by column 3. So I'm making two operations. First of all, column 1 by column 3 and then column 2 by column 3. So how many times am I doing that operation? That interchange is happening twice. So when it happens for the first time, a negative sign comes. But when it happens for the second time, another negative over that negative will come, and negative will make it positive. Did you get my point, students, here? So let's bother about the negative sign here. Negative sign will come as long as you're having the number of observations, number of operations are odd. If the number of operations are even, there will be no negative signs. What I'm trying to make you understand is the negative sign depends that how many times have you performed this interchange. But understand that you cannot just do this interchanging row and column wise in a mixed manner. Either you perform such interchanging first of all row by row, and once you have done this, then you can start performing interchanging column by column, but you cannot do it simultaneously. That interchanging row by row and column by column, you have started doing it all together. Well, that you should avoid. I hope you're understanding why it will create havoc. So what you understand here is that interchanging must be done very cautiously, because here you need to be careful that the sign, negative sign, comes into picture. Did you get this particular part, students? Let's move to the next property then. I'll give you more clarity with some more example. Let's say if you are having this A1, B1, C1, then you are having this A2, B2, C2, and then you are having this A3, B3, C3, right? And if I'm performing an operation, let's say I'm interchanging column 2 by column 3. So what will happen? Let's say if it was a determinant A, how many times I'm performing this operation? Only once. So a negative sign will come into picture. So this will be the value here will be negative of it. So if you want to call it A, then I'm supposed to put a negative sign over here, and I can make this change happen, column 2 by column 3. So column 2 by column 3, second column, third column, they can be interchanged. First column will remain intact, A2, A1, A2, A3, but this third column will come in place of second column, and the second column will go at the place of third column. So this is how things will happen, and that's how you need to understand that this is what is going to happen here with the determinants. So did you understand this second property? How can you interchange rows and columns, row by row and a column by column? Let us now look at the next property to understand it more clearly, that what all we can do as far as determinants are considered. Third property, it says if two rows or columns for a determinant are identical, then the value of the determinant is 0. Why is it 0? I'll explain it now. But before that, have you understood this particular result? The moment you see that any determinant has two rows identical or two columns identical, then you can very, very clearly, unhesitatingly say that the value of the determinant will be 0. Here, if you look at this part closely, A1, B1, C1 and A1, B1, C1, I can see it there in the first and third row. So here, first and third row are identical. I can very clearly say that this determinant will be 0. Why? Let me explain this part more clearly. Say that this is delta, which is this determinant, right? Now, if I perform an operation, which operation? I am interchanging row 1 by row 3. So if I interchange row 1 by row 3, what am I supposed to do? What will I get? I'll get A1, B1, C1 here, and this A1, B1, C1 here, which are identical actually, and then A2, B2, C2 in the second row. But this is also delta. But as per our understanding, if a row is interchanged by another row, it becomes negative. So delta is equal to negative delta. If a number is equal to its negative, well, that's possible only when the number is 0. Do you get my point? If delta is equal to minus delta, then that can happen only when delta is 0. So that's exactly what I'm trying to make you understand, is remember the learning that if two rows or two columns of a determinant are identical, then its value is 0. That's your property number 3. I hope you will straight away remember this. Let's talk about the next property. What does it say? This property is again a crucial one. If the elements of any row or any column of a determinant be each multiplied by a same factor k, then the value of the determinant is also multiplied by k. What did I just say? I'll try and make you understand it first, then we'll talk about this later. Let's say there is a determinant delta and it has certain elements. There is a determinant delta, let's say, and it has certain elements A, B, C, D, E, F, G, H, I, right? So this is the determinant over here. Now let's say I am willing to multiply any row or any column by any number. Let's say there is a requirement, which you'll start understanding while dealing questions based on determinants. So there is a requirement arises which says that you got to multiply any row or any column by a certain fixed value. Let's say I'm supposed to do it. Well, that can be done. That can be done when you divide also this particular determinant by that same value. So what I'm trying to make you understand here is, let's say I can write a 2 by 2 here. Yes, we can. So if I'm writing a 2 by 2 here, the numerator 2 I'm pushing inside, the 2 in the numerator I'm pushing inside, and the 2 in the denominator I'm keeping outside. And that 2 which you're pushing inside, the numerators 2, that can be pushed with any column or any row. What I'm trying to make you understand is that, let's say this is your delta, but I want a number to be multiplied to either any row or any column. Well, that can be done first, yes, but if you're willing to multiply any row or any column by a number, then you got to divide this determinant by that same value so that it remains balanced. I hope you're getting it. Now, how to do that? Say I am multiplying it by k, so I got to divide it by k so that the value remains same. Now this numerator's k, if I want to push inside, I need to ensure that it goes to either any row or any column. That's what you can do. For example, let's say as per the requirement of the question, I choose that this k goes to the second column. Well, in that case, A, D, G will remain same. But here when k goes to the second column, KB, what is happening here? KB, then KE, then KH. Then again, you will have the third column intact. What is that? C, F, I. Did you get that part? So this thing which you're willing to multiply, that thing, that factor can be multiplied to either any row or any column. That's what I'm trying to make you understand. Vice versa is also true. What do I mean by vice versa? If you wish to take something common, if you wish to take something out from a determinant, well, that thing can be taken out of the determinant from either any row or any column. What does this mean? This simply means that, let's say if I have a determinant over here, let's say 2, 4, 6, 1, 3, 7 and 5, 8, 9. So I can see that the first row has a factor 2, 2, 2. Well, that can be taken common. So any number from any row or any column can be taken common. I hope you're getting it. So if this is delta, well, delta will be 2, 2, 2 common from the first row. Then I'll be left with 1, 2, 3 and then 1, 3, 7, 1, 3, 7 and then 5, 8, 9. So this is what I'm trying to make you understand, that this is what you can do with this property of the determinant if you wish to multiply something inside, if you want to take something out. So it goes or comes out from either one row or one column. That's what you need to remember from this properties context. But in matrices, this is a completely different story. When you wish to multiply a matrix with a certain scalar, that scalar gets multiplied to all the elements of that matrix. So matrix and determinants are different in altogether in a complete sense. You need not merge them. But of course, they have some similarities which we'll keep on discussing. But as of now, when you wish to multiply a determinant by a scalar, that number which you are willing to multiply with will go to either any row or a column. I hope this part will be remembered by you all. Now, if this property is understood by you all, there comes another property which again plays a very crucial role in solving a lot of questions. I'll straight away demonstrate you that how easy questions become if you know such properties. What does it say? If every element of some column or row is the sum of two items, if every, right, then the determinant is equal to sum of two determinants, one containing one of the first term in place, the other only the second term. What does it mean? let's say here in this determinant, I had this thing, these elements. Which elements? A1x, A1 plus x, A2 plus y, A3 plus z. This is what I had. And then I had B1, B2, B3, and then C1, C2, C3. Well, this determinant can be written as A1, B1, C1, A2, B2, C2, A3, B3, C3, plus X, B1, C1, Y, B2, C2, Z, B3, C3. Did you get it? How am I splitting two determinants? Similarly, are you getting this idea that how are determinants added? Determinants are added only when, for example, this is a determinant of order 3, right? This is a determinant of order 3. So if I am given two determinants, let's say if I am given two determinants, for example, this is what I'm given, right? I'll just take you with an example. Let's say if I'm given 2, 3, 7, 4, 5, 8, 1, 2, 9, right? This is a determinant we are given. This is the determinant of order 3. And I'm asked to add it with some other determinant. Well, I can add this determinant with some other determinant only when if this determinant has either two rows matching with that other determinant or two columns matching with that other determinant. Or what you can do is you are perfectly allowed to find the value of this determinant separately and the value of this determinant separately and then add them up. So you have two choices. For example, if I'm given, let's say 2, 3, 7 remains as it is, 1, 2, 9 remain as it is. But here, let's say I'm given 1, 7 and 0. So what am I given here is, if you just pay attention to this particular part, first row identical, third row identical. So if first row in both of the determinants, third row in both of the determinants are identical, I can add their second rows, the elements of the second rows, corresponding second row, and then I can find the, write the result, the addition of these two determinants. So addition or subtraction of determinant is possible if let's take the example and understand it better. If this was the determinant of order 3, I can add or subtract these two determinants, but if order 3 has at least either two row or two columns similar in both the determinants. Are you getting my language very clearly? Both of these determinants were of order 3. I wanted to either add or subtract them. So I needed to ensure that at least either two rows or two columns are identical. Then only I could add or subtract them. And how does that addition or subtraction takes place? You got to add or subtract the corresponding elements of that third unequal row or column. So here it was this row which was unequal one. So I got to simply add the corresponding elements. And how will I do that? The addition will be very simple, students. First row and third row will remain intact. They will remain as it is. So it will be 2, 3. I'm really sorry. I did not notice it. So it will be, first row will be 2, 3, 7, 2, 3, 7 in both the cases. Third row was 1, 2, 9, 1, 2, 9 in both the cases. Now, what do you do with the second row? Second row will be 4 plus 1, 5, 5 plus 7, 12 and 8 plus 0, 8. I am giving you a very good complete clarity that either you expand this and then you expand this and then you add them up. You will get a result, or you expand this and you will get a result. Both of the results will be same. So did you understand addition of determinants, subtraction of determinants? That's exactly what we tried explaining you with this particular example, that if you are given a determinant, it can be broken into addition or subtraction of two determinants in this manner only. I hope you have understood it with this illustration in a more clearer manner. With that, let's move further with the next property. What does the next property say? The next property says, I hope this property is very well understood by you all, the addition of the determinant or subtraction of the determinant. You're supposed to put the minus sign if it is the case of subtraction here. Well, here, next property, what does it say? Look at this. The value of the determinant, look at this part, here comes the most crucial part, does not change The value of the determinant does not change. When? If the elements of any row or column, either I'll do the operation row by row or column by column. So let's say I have chosen to operate row by row. So the value of the determinant does not change if the elements of any row are increased or decreased by equimultiples of the corresponding elements of any other row. Sir, we didn't understand anything at all. This is very confusing. Trust me, this is the most simplest definition you can have, but I'll try to explain it with one apt illustration so that you get it more clearly. Understand this part. Here, let's say I'll go opposite. I am given this determinant here, let's call it delta, right? So we have this determinant over here and we are calling it delta. Okay, students, so this determinant here is, let's say, delta. A1, B1, C1, A2, B2, C2, and A3, B3, C3. As per this property, what is it trying to say? This property says that if I were to apply an operation on a column, let's say, so I'm applying the operation on column 1. Now, what operation is being done? What substitution will be done? What replacement will be done? So I'll be doing that replacement on column 1. So whatever operation I'm doing, that operation will happen on column 1. So column 1 will get changed, column 1 will get replaced. So A1, A2, A3 will get replaced. Now what replacement will come here? That replacement is, I will replace column 1 by column 1 plus m times column 2 plus n times column 3. What does it mean? Now you will realize those useful operations which I was discussing before discussing these properties of determinants. You will realize the importance of those useful properties, useful operations now. Have a look at this part. What I'm trying to make you understand is, have column 1, which is A1, multiply M2 column 2, let's say MB1, and then multiply column 3 by N, so NC1. In the first row, this will happen. So what will I have? As the first element of first row in column 1, what will I have here? A1 plus MV1 plus NC2. And that value will get replaced here in place of A1. That's exactly what this operation means. Well, this is not simply just an operation, but it means that if such operations are being done, the value of the determinant remains same. It does not change. Did you get that part? Similarly, A2 plus MB2 plus NC2 will appear here in place of A2, and similarly A3 plus MB3 plus NC3 will appear here in place of A3, and again the value of the determinant will remain intact after this particular operation. I hope you have understood it. What you need to understand here is something very crucial, that when you apply such operations, you need to be a little more cautious and alert that there are certain constraints which you should be aware of. Sir, what are those constraints? I mean, should we take care of something else as well? Yes. There are some things which are not said in this property, which students themselves assume, and that's where they commit the error. Now, what is that area where students are prone to commit mistakes? That is what I'll be discussing. But before I go to that part, give me a clarity that have you understood this property, how to use it? Now let's talk about that part, that how can you not miss it. But before I come to that part, let's solve a question by using this particular property, and then we'll come to that part. Let's solve this particular question asked by JEE Mains in 2021. So let's solve this particular question, and then we will discuss this sixth property in a more detailed format, where I'll be telling you that what are the errors students are prone to commit, which you should not, which you should avoid. That's the area where you should be more cautious, more alert, and more proactive. What is that? Let us discuss this question first, and then we'll come to that part. What does this question say? It says you need to find the solution of this equation. So there is an equation given to you, and you need to find its solutions, where we are told that x lies between 0 to pi. Okay, we'll talk about that later, but this is something which is needed to be solved. Okay, sir. Okay, we'll do that. Now, you have two choices. Either you straight away get into this question, you expand the determinant a trigonometric equation will get formed and then you solve it and get the answer. Sir, can we do that? Of course. If you were not aware of the properties of the determinants, you are always allowed to do that, and anyways you can always do that. But after understanding the properties, after knowing the properties, do you really think that you should straight away, go ahead with the expansion of the determinant? Should you not work on the simplification of the determinant, which you have learned through the properties which we have discussed so far? So if I know certain properties, can I apply those properties here in this question before straight away expanding this determinant? Yes, we can. Let's go ahead with that part. How? Look at this question asked by JEE Mains in 2021. It says, what are the solutions of this equation? Okay, I can clearly see that ultimately I need to expand it. So let's try and simplify this. What I can see is sine square x, sine square x, sine square x, cos square x, cos square x, cos square x, sine 2x, sine 2x, sine 2x. Even 4 times sine 2x, 4 times sine 2x, 4 times sine 2x. So I think, sir, you should do something. If you do something, you may end up getting a better result with more efficiency or efficacy. How? Let's work on that. So I'll be applying two operations here. First operation here, I'll be applying on, let's say, row 1. So on row 1, I am applying an operation that from row 1, I am subtracting row 2. Simultaneously, I am performing one more operation, which is on row 2, I am performing another operation that from row 2, I'll be subtracting row 3. So the conditions, the constraints, the limitations which I was talking about have come into picture. The first constraint which you should stay aware of is that don't apply operations on rows and columns simultaneously. Let's say here, if I have applied this operation on rows, the second operation also is being applied on the rows. I haven't applied the second operation on columns simultaneously. So at a time, either you apply operations on rows or columns, but don't apply operations on both simultaneously. That will again create a havoc and you'll get incorrect answers. First limitation, I hope, is understood by you all through this example only. Second limitation, please understand, what was the order of this determinant? Sir, the order of the determinant was 3. Yes, the order of the determinant was 3. Well, in that case, the number of operations at a time can be applied should be order minus 1. Did you get my language? My statement was very simple. Order was 3. What is 3 minus 1? 2. So at a time, the maximum number of operations which you can think of is 2. Did you get that part, students, very clearly? I hope you are getting it. If the order is 3, the maximum operations I can apply at a time are 2. Later on in the next step, if I wish to multiply more operations, I can, but at most 2. And those 2 should also be either row by row or column by column, but not both simultaneously. I hope you are getting more clarity about the limitations which we are discussing right now through this question. So let us start simplifying this determinant here. So what do I get? So here, row 1 minus row 2. What will I get? Row 1 minus row 2, right, students? So row 1 minus row 2, 1 plus sine square x. I'm really sorry. It should not be row 1 minus row 2. I have mistakenly written it. It should have been column 1. Sorry. I did not notice it. I mistakenly went ahead with row. Actually, the same thing which I was suggesting should be done column by column, which means in column 1, I'll subtract column 2 from column 1. I hope you can see. Why am I doing it? Because sine square x will eliminate sine square x, cos square x will eliminate cos square x, 4 sine 2x will eliminate 4 sine 2x. So the motive or the intent remains simple. I'll try to minimize this expression. I'll try to have lesser number of terms in this particular expression, and I'll try to maximize the number of zeros, because the more zeros you have in a determinant, its expansion becomes more easier. I hope you are able to calculate it in your brain. So first operation I'll do is I'll subtract column 2 from column 1, and the second operation will be I'll subtract column 3 from column 2. I hope you're getting the logic. Sine square x, cos square x, and 4 sine 2x. Again, I'll have lesser number of terms, more number of zeros probably. So that's exactly what my motive is. So here, 1 plus sine square x minus sine square x will be 1. Cos square x minus 1 minus cos square x, cos square x, cos square x are cancelled. I'm left with minus 1. 4 sine 2x minus 4 sine 2x, I'm left with 0. Are you understanding how simple it is becoming? And that's exactly what our motive or intent should be. Next, what do I have next? Here, from column 2, I'm subtracting column 3. So sine square x minus sine square x leaves us with 0. 1 plus cos square x minus cos square x leaves us with 1. 4 sine 2x minus 1 minus 4 sine 2x leaves us with a 1 here. Everyone with me so far? Third column will remain intact because I hope you remember at a time maximum only 2 operations can be done simultaneously because the order is 3. Right, students? So column 3 will remain as it is. It will have sine square x. It will have cos square x. And the third term will be 1 plus 4 sine 2x. I hope no confusion on that. Now it's the time that you expand it. Now either you use the Sarrus rule or you expand it along with any row or any column, whatever you wish to do, you can do that. So this is what we are now dealing with. How do I expand it? Let's expand it with respect to any row or any column. I think that will be more appropriate. So let's say I'm expanding it along with row 1. So I'm expanding it along with row 1. So how do we do that? I'll write the elements of row 1 and then I'll multiply those elements with the cofactors of those corresponding elements and then I'll add all those results. That's how you will get the expansion of the determinant. That will be the value of the determinant, right? So here, first of all, I'll write this 1 times. So I'll remove this 1 column and the row which contains 1. So I'm left with this and this. So this gives you 1 plus 4 times sine 2x and this gives you minus of minus cos square x, which is plus cos square x. So that is what you get from here. Then minus 0 times something. So 0 times cofactor of 0 will be ultimately 0 because 0 is getting multiplied to it. So I'll not bother about this term. Then plus minus plus. So again, I'm supposed to use a plus sign here. So plus times sine square x times. What am I supposed to do? Column and row. Then what am I left with? Minus 1 into minus 1. That will be plus 1. Minus here 0 into anything will be 0. So that I need not bother about. And this expression is given to be 0. So this is what we need to solve further, right? I hope there is no confusion on that. So here, when I proceed further, what do I have here? Let's look at that part in a more clearer manner. I hope this is what we know. This is what we have. Column 1 minus column 2, sine square x, sine square is getting cancelled 1. This is minus 1, this is 0. Then 0, 1 and then minus 1, I believe. Yes, and this remains as it is. With 1, it should be 1 plus 4 sine 2x plus cos square x. Yes, 0 does not do anything. And then sine square x leaves you with 1 minus 0. Yes, we are going great. No confusions on that, I believe so. Then I hope you can see here, I'm left with 1 plus 4 sine 2x. Okay, so I'll leave it as it is. There you have this 1 plus 4 sine 2x. Then what do we have? We have cos square x plus sine square x, which we all know is nothing but what? I think 1. So cos square x plus sine square x is another 1. So that is another 1 you have is equal to 0. Now what is next? I think the answer is next because 1 plus 1 is 2. So 4 sine 2x is equal to minus 2, which gives you sine 2x is equal to minus 1 by 2. Now let's try and generalize this result. X we are told to be lying between 0 and pi. Okay, we'll work on that. X is lying between 0 and pi. Can I say from here sine 2x is equal to minus 1 by 2? Can you talk about 1 by 2? Yes. What is 1 by 2? 1 by 2 is sine 30 degree, which means sine pi by 6. Sine pi by 6, right? So if I wish to write it as, can I write it as sine pi minus pi by 6? Because sine pi minus pi by 6 is equal to minus sine pi by 6. I hope you know this quadrant theory, which I'm suggesting here is, I'm really sorry, it's not sine pi minus pi by 6. I should have said pi plus pi by 6 because this is pi plus pi by 6 will throw you in the third quadrant, and in the third quadrant sign remains negative. This is the quadrant theory which you study when we discuss trigonometric ratios, identities and equations. So here I can write it as sine pi plus pi by 6, right? So that's the conclusion we have. I hope there is no confusion on this, that how did we get this part, pi plus pi by 6. Are you all with me so far? No confusions on that. Similarly, if I subtract See, this is 0, then pi by 2, then pi, then 3 pi by 2, then this is 2 pi as well. So if I subtract pi by 6 from 2 pi, then also I stay in the fourth quadrant. And in the fourth quadrant, sign is negative, because sign remains positive in first and second. It remains negative in third and fourth. So I could have written it either like this, or I could have written it as sine 2x is equal to sine 2 pi minus pi by 6. Although with this also you can get the answer, or if you wish to use this, you can get the answer. Totally up to you, whichever method you wish to use. From here, I'll say that sine 2x is equal to sine pi plus pi by 6, which is sine 6 pi plus pi, 7 pi by 6. So from here you can use the general solution, or from here also you can use the general solution that sine 2x will be equal to sine 2 pi minus pi by 6 is 12 minus 1, which is 11 pi by 6, right? So from here also you can use the general solution. Well, forget all this. Now, let's look at the options. So I am seeing certain options, and what I need to ensure is that whatever value of x I receive, that value should lie between 0 to pi. I hope no confusions on that. Also, I need to ensure, chalo, forget this. Let's work on this particular result. I am either going to use this or both, and I'll get the answer, right? So we know one more conclusion, that if you ever get sine theta is equal to sine alpha, do you know how to write the general solution? The general solution is theta is equal to n pi plus minus 1 to the power n alpha. This is the general solution if sine theta is equal to sine alpha. If you don't know this, if you don't remember it, if you are not able to recall it, don't worry, we will discuss it when we discuss trigonometric equations and their solutions. General solution is what we'll be discussing, then we'll be coming up with this particular formula. Don't worry about it. But if you have learnt it at this stage, take a note of it and try to remember it. Now, let us get back to what we are discussing here. So, what I'm trying to make you understand here is a very simple result is sine theta is equals to sine alpha. Theta is n pi plus minus 1 to the power n times alpha. So sine 2x is equals to sine 7 pi by 6. So by that, 2x should be equal to n pi plus minus 1 to the power n, and then you have 7 pi by 6. Right. Now start putting certain values of n and you'll start getting the answers. Even if I wish to have, I can have this x here as n pi by 2 plus minus 1 to the power n, 7 pi by 6 into 2, that is 12. So I'll start putting certain values and I'll start getting the answers. But while achieving or getting those answers, I'll keep ensuring that whatever value of x I'm receiving, that should lie between 0 and pi. So let's begin with this result, that should I put n is equal to 0? If I try n as 0, this will be 0, minus 1 to the power 0 will be 1. So I'll get the first result as 7 pi by 12. So first conclusion will be 7 pi by 12, which I think is the correct answer, because 7 pi by 12 is less than pi, because if it is 12 pi by 12, it would have been 12. So 7 pi by 12 is of course less than pi. That's perfectly an acceptable answer. Well, what's next? Next will be, let's try the value of n as 1. So if I try the value of n as 1, I'm putting here n as 1 here. So if n is 1, x will be 1 into pi by 2, that is pi by 2. If 1 is put here, it should be minus 7 pi by 12, somewhat like this. I hope there is no confusion on that. So here to make a 12 LCM here, this is 6. I'll multiply in the numerator and denominator, and from here I can very clearly see that it will give me minus pi by 12, which could have been the answer, but this is not an acceptable answer because x should be between 0 and pi, and this is less than 0, unacceptable. Now let's try the value of n as 2. So I'm putting the value of n as 2 here. So if I put n as 2 here, what will I get? X is equal to 2 pi by 2, that will be pi, plus minus 1 to the power 2 is of course clearly we know 1, plus 7 pi by 12, right students? And that will give me a value which I think will create some problem, may create some problem, because here 12 pi plus 7 pi. So 12 pi plus 7 pi will be 19 pi. And well, in that case, 19 pi by 12 should also not be accepted because this is greater than pi. So I think n is equal to 2 creates some problem which should not be an acceptable value. But here to me it looks like, had I tried 11 pi by 6, can I create 11 pi by 6 by some means? So let us try another value which I'm going to try with n being 3. So let us try the value of n as 3. So if I try the value of n as 3, the value of x is going to be 3 pi by 2 minus 1 to the power 3 will be minus 1 minus 7 pi by 12, right students? I hope no confusions on that. Now when I wish to have the next part, can I say to make it 12, I'll multiply it by 6. So 6 into 2 is 12 and 6 into 3 is I think 18. What is 18 minus 7? 18 minus 7 is I think 11 pi by 12. So yes, that is again an acceptable value, and this is the boundary value we can have because next value may be greater than pi. So 11 pi by 12 is another acceptable value which we may have received from here as well. The next conclusion we had drawn, because if 2x was 11 pi by 6, x would have been 11 pi by 12. Are you getting it? So from here, I think I'm getting two conclusions. One is 7 pi by 12, another is 11 by 12. Amazing question, great question, perfect question which clubs two concepts, determinants and trigonometry. Did you get that part? I hope a great clarity is attained by you, how to use properties, how to expand the determinant, how to apply trigonometry, the general solution. Everything is discussed in this one particular question, and that's exactly what we have been emphasizing upon. Focus on solving great quality of questions. Even a good single question is equal to 10 bad questions, and that's exactly what you're supposed to do. Instead of solving a lot of questions and bragging about it that you have done thousands of questions, I will always on any day say solve good questions. Even lesser number of good questions are equivalent to a lot of bad questions, and that's exactly what we are emphasizing upon. So focus on such questions, right students? With that, what do we have next? Let us proceed ahead and let's understand what gets unfolded. Now, let's move to the next property. What does it say? The next property says that if each element on one side or the other side or both sides of the principal diagonal determinant is 0, then the value of the determinant is the product of the principal diagonal element. What does it mean? It means, let's say you have this ABC as the principal diagonal, and either of this, either 0, 0, 0 are found here, or this principal diagonal is here, 0, 0, 0 are found here, or either on both sides. Let's say principal diagonal is this ABC, 0, 0, 0, 0, 0, 0 are found on both these sides. Even if these zeros exist on either of these sides, I hope you're getting my word very clearly. In that case, the value of the determinant is the product of the principal diagonal elements, which is this ABC. Did you get that part very clearly, students? I hope there is no confusion on this. I am very clearly mentioning this part time and again, that the part remains simple. All you got to do is the simple thing, the very simple thing. What is that? That if you ever encounter a upper triangular matrix or a lower triangular matrix. So I'm relating it with the context of matrices. What does matrices say? You will have square matrices, and then you will have either an upper triangular matrix or a lower triangular matrix, or both. In that case, if you want to take the determinant of that square matrix, which is either upper triangular matrix or a lower triangular matrix, the determinant of such matrix is always equal to the product of its principal diagonals elements. That's exactly what I'm trying to say here. The same concept in the context of determinants, if expanded or understood, what does it mean? What does it imply? The logic remains very simple, students. It is very straightforward, that I hope you can see it very clearly. Either 0 zeros were found here above the principal diagonal, or all the zeros were found here below the principal diagonal, or on the both the sides, either below or above. Well, in such cases, the value of the determinant will always be equal to the product of the principal diagonal elements. Do you understand this particular part? I hope this property makes a lot of sense. And are you understanding and realizing that if you stick to these properties, if you remember these properties, expansion of determinant looks very simple. Even if you expand by looking at this, this is very simple. Let's say I wish to expand it along with the first row. What will happen if I wish to expand it along with the first row? A times BC minus 0 plus 0 into something plus 0 into something. I hope you are getting. A times BC minus 0 will be ABC, and that's all we were having. So even if you wish to do that, that can be done. But even some fractions of 5 to 10 seconds of calculation can be saved if you know this property and if you understand this observation. So remember this also as a result and apply it in your questions. You will get such quick results. Now, what constraints I'm talking about, what conditions, what limitations you have while applying these properties, that row or column operation you should stay aware of. First condition, that it should be noted that while applying operations on determinants, that at least one row or column must remain unchanged. As we have already discussed, at least one row or one column must remain unchanged. That's exactly what I'm saying. Let's say if there are 3 rows and 3 columns, basically the order is 3, the determinants order, right? So the number of operations on either rows or columns you can apply would be 2. 1 less than 3. Why? Because at least one row or one column must remain unchanged. That's the first condition, first limitation students forget. And sometimes what they do is they apply operations on all the 3 rows or on the 3 columns simultaneously. And that's where they commit the mistake. I hope you are getting this part very clearly. So adhere to this part. Remember this, that maximum n minus 1 number of operations can be performed. What is n? The order of the determinant. Second conclusion, maximum number of operations at a time, order minus 1. That's exactly what it means. Third conclusion, it should be noted that if the row which is changed by multiplied by a non-zero number, then the determinant will be divided by that number. That is again a very simple property. We have already learnt it, but if you have forgotten it, I'll try and make you understand with this particular example, that if you are having a determinant here, which let's say is A, B, C, D, right? That's your determinant. Let's say we are calling it delta. And there is a need arises which says that you are supposed to multiply this second row by a certain number scalar quantity k. I need to multiply to make my calculation simpler. Well, can we do that? Yes. But if I have done that, I'm supposed to divide this determinant by that scalar, by that same scalar, which means if I am multiplying this k inside to the second row, where I'll be writing it as AB, CK and DK, well, in that case, I need to divide this determinant by that same scalar, which means I should put a 1 by k here. Did you get this part? As we have already discussed this, that any row or any column can be multiplied by a scalar, but that scalar should be there in the division as well, so that the value of the determinant remains intact. It remains balanced. I hope you have learned that result as well. Now, there are certain observations. If you remember, you will get certain results very easily. These are some standard determinants which I'm putting right there in front of you, and I'm in a very straightforward manner asking you to remember these results. Now, what are these results? Let's look at them one after another. If you are given any determinant of this sort, 1a square, 1b square, 1c square, sometimes you may deal with 1x square, 1y square, 1z square, 1 alpha square, 1 beta square, 1 gamma square. In that case, either you wish to apply it, either if you wish to expand it with the help of Sarrus rule or any row or column, or if you want to apply any property of the determinant and then you expand, the final outcome is going to be this cyclic result, this circulant result, which is a minus b times b minus c times c minus a. So of course this can be explained with the derivation, that I'll give you the complete explanation, the expansion, and then I'll come up with this result. But in this one shot, I'm skipping that part and I'm directly giving you that this is one of those crucial results which you are supposed to memorize or remember. So this is a learning which you, if you keep with yourself, you can save a lot of time in the examination and can directly write the result. There are questions which use this particular expression. So while solving, let's say, a particular question, you may end up getting this particular expression. Now, after further 4-5 steps of solving, you will get this as a result, which I am wanting you to skip. And remember that whenever you encounter something like this, do write this. What did I say? 1a square, 1b square, 1c square. If you wish to take the determinant of it, straight away, substitute or replace it by a minus b times b minus c times c minus a. Remember this as a result. What is the next result you are supposed to remember? Next result is, if you have ABC, a square, b square, c square, and bc, ca, ab, well, that is equal to 111 a square, b square, c square, and e cube, b cube, c cube. First of all, I'll explain how did that happen, and then I'll take you to this particular result. What is this result, or where is this result coming from? Let's have a look at that. Please understand. Let's say if I multiply the first column by a. Can I do that? We can. So here I have ABC, a square, b square, c square, and bc, ca, ab. So I have a, b, c, right? Then what did I have? A square, b square, c square. Then what did I have? bc, ca, right? And then ab. And this is the determinant, let's say, delta we are dealing with. Now what did I do? First of all, I am multiplying the first column by a. I am seeing something which you may not have noticed right now, but I am multiplying first column by a. When you multiply first column by a, the rule says you got to divide it by a. So I am dividing it by a here, and I'm multiplying it by a here. So a square, this becomes, this thing becomes here this thing becomes a cube, and here it becomes abc. The second column I am multiplying by b. If I multiply the second column by b, this will become b square, this will become b cube, and here it will become again cab, which can be written as abc. But if I have multiplied the second column by b, I got to divide this determinant by b, which I'm putting here. In the same fashion, I'm multiplying the third column by c, so I got to divide that by c. So that will make it c square, then c cube, which I'm writing more clearly here. So I'm writing it as c cube, and there you'll get abc. Are you noticing something? Are you observing something? Are you seeing a property being used? The property is ABC, ABC, ABC can be taken common outside. So if I take this ABC, ABC, ABC common, I hope you know from any row or any column, the same element can be taken common. The way you multiply, the way you take common, the same vice versa process. So if I take this ABC, ABC, ABC common, here I'll be left with 1, 1, 1. I hope you're getting this result very clearly. So here I'll be left with 1, 1 and 1. But that ABC comes outside and cancels this ABC. Now what do we do? To make something like this, can I first of all apply an operation? What does that operation say? That I am interchanging row 1 with row 2. But as we have discussed, when you interchange a row with another row, negative sign comes to balance it. I hope you remember it. So first of all, I'm removing this ABC from here. So this ABC is removed from this ABC. So this is your delta basically. But when you're interchanging row 1 by row 2, basically a negative sign should come here. So here second row will have a square, b square, c square, and the first row will have a cube, b cube, c cube, right? So here I'll write a cube, b cube, c cube in the first row, and the second row will have a square, b square, c square. Now I still haven't attained what I'm supposed to attain. So the next row operation I'm going to do is, I'll interchange row 1 by row 3. So I'll perform another operation, row 1 by row 3. And when you interchange row 1 by row 3, this minus will become plus, and then row 1 will get interchanged by row 3, and that's where row 1 will have 1, 1, 1, and row 3 will have a cube, b cube, and c cube. So did you get that part where I was constantly emphasizing and mentioning that remember and learn these properties, interchanging the rows, applying a determinant by a scalar quantity and then taking common it, and then this is how you have converted this particular result into this. So sometimes this is also what you need to do. Anyways, what you should remember as a result is, what you must remember as a result is that whenever you encounter something like this or something like this, something like what? Something like 1, 1, 1, a square, b square, c square, a cube, b cube, c cube, or abc, a square, b square, c square, bc, c, ab, then its expansion is somewhat similar to this, and additional to it, you will have another factor ab plus bc plus ca, which means it will be a minus b times b minus c times c minus a times whole of ab plus bc plus ca. That's what I'm trying to make you understand. Now, let us understand some more circulant determinants. These are some standard results which are taught to you whilst in the board examinations. You understand all the expansions, you understand all the results, you apply all these properties. But here, from JEE's perspective, I am not coming up with all the derivations, all the expansions of these results. I am directly giving you that this is what it is and use it like this only. And if you can memorize, try to memorize as many as you can. Try to memorize as many as you can. For example, look at this part. I hope you can see a lot of similarity here, and this can again be proved by using the same logic which we have done here. You can take ABC, ABC, ABC common from here, and then same result can be generalized here or generated here. So these two can be converted by using the properties as we have already discussed, which we are not discussing again. But what you need to remember is, whenever you deal with either ABC, BC, CAB, ABC, 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 or ABC, A square, B square, C square, A cube, B cube, C cube, in such cases, the expansion looks like ABC times A minus B, B minus C, C minus A. Why? Because when you take this ABC, ABC common, it will become exactly what we have discussed here in these cases. I hope you are getting this complete clarity with the help of this part. Let's talk about the next part, fourth part. These are some general results. This can be treated as a cheat sheet. I will emphasize that you take the screenshot here of this part, and before this part, and learn these results, because these results are some very crucial results which will actually help you in your real examination. If you have these results with you, you can directly solve a lot of questions without actually expanding them. Sir, what if we don't remember them? Then expand. How? Use properties, the properties which we have discussed. Sir, if we forget the property, if we are not able to apply the property, use Sarrus rules, or expand it with respect to any row or any column. You will somehow eventually will get these results. Don't worry about it. You're bound to get them. That's exactly what I'm trying to mention. But if you can remember these results, which are very commonly, very widely, very repeatedly used, then why not? If remembering or learning these results will help you in the real examination hall, then you should invest some time in learning them. Because right now, before your first attempt, you have certain amount of time through which you can memorize them. So why should you not invest some time in learning and memorizing them? If you have these results at your fingertips, you will be able to apply these results directly in your examination hall and get the answers. And that's exactly what any student who scores a good mark, a percentile, does. You should also do that. Now, let's talk about this part. 1, 1, 1, ABC, A cube, B cube, C cube. Symmetry is there, cyclicity is there, they are circulant determinants, and here also this is expanded as A minus B, B minus C, C minus A times whole of A plus B plus C. Something which comes into picture a lot many times is this particular result, students. This is something I want you all to remember. This you must remember. Forget all the other ones. Even if you forget them, I don't know how can they be utilized or not. That's a different story. But this is something which is a must for you all to remember by heart or memorize. What is it? ABC, BCA, CAB. ABC, then BCA, then CAB is equal to A cube plus B cube plus C cube minus 3ABC. And in the quadratic equations, we have already learnt A cube plus B cube plus C cube minus 3ABC is equal to whole of A plus B plus C times whole of A square plus B square plus C square minus AB minus BC minus CA. So that result needs to be remembered by you. Please, always And I hope you know, if a plus b plus c is 0, well, in that case, a cube plus b cube plus c cube is equal to 3abc, because a cube plus b cube plus c cube minus 3abc will be 0. Well, what does it mean? It means abc, bc and cab, this determinant will be equal to 0 if a plus b plus c is equal to 0. These are some very important results which we have discovered and explored so far, and I'm sure you will remember them. Will you remember minimum at least this particular result? And of course, all the other results will be bonus for you if you could by heart them. After this, let us see what do we have next. So what is the next part? Let's talk about that particular portion. So here we have another question right there in front of us, asked by JEE Mains and Advanced 1985. So that much previous question are we discussing right now? Trust me, everything is important, everything is crucial if it is having something relevant to your examination. So JEE Advanced in 1985 has asked a beautiful question. Why am I calling it a beautiful question? Because this question is using concepts of two chapters, vectors in 3D along with determinants. How? Let's have a look at that. First of all, let's understand this particular question, which uses the concepts which we have learned so far, and I'll tell you that within seconds, how can you crack questions if you know the concepts. And if you keep looking at the patterns, questions asked by JEE Advanced way back are now being asked by JEE Mains. So sometimes JEE Mains repeats the question as it is, verbatim, without any change, asked by JEE Advanced way years back. So I hope you are understanding. Advanced has its own importance and significance. Let's have a look at this particular question. It says that this is equal to 0. Okay, we don't know this, nor we know much about this, but let's keep it with us. Then it says that there are three vectors. Right. Now, these vectors are written in a different format. It means I cap plus aj cap plus a square k cap. Another vector is I cap plus bj cap plus b square k cap. The third vector is I cap plus cj cap plus c square k cap. So these are the three vectors, and we are told that they are non-coplanar. Now, there comes a condition of coplanarity, which we'll discuss in the chapter vectors in 3D. But as of now, we'll reveal it that what does it mean. But what they're asking you, the value of the product ABC. Sir, how do we solve this particular question? We don't know nothing much about this vectors and all. How do we do that? Trust me, whenever somebody says that these three vectors are coplanar or non-coplanar, when they are coplanar, their determinant is 0. So if they are said to be non-coplanar, what does it mean? Their determinant will be non-zero. What does it mean? So first of all, you should be able to conclude that there comes a deduction that the coefficients of I cap, j cap and k cap, what are they? 1 a square, 1 b square and 1 c square. This determinant will be non-zero. Why? Because these three vectors are non-coplanar. Had they been coplanar, their determinant would have been 0. So first of all, from question, what I know is 1 a square, 1 b square. I think I'm writing it correctly. Yes, and then 1 c square. This determinant will not be 0 because these three vectors are non-coplanar. This part I hope is understood by you all. If you are not able to digest this particular part, have patience. We'll talk about this when we discuss the chapter vectors. Don't worry about that. Now, let me come to this particular question. The expression we are given here is this: a square 1 plus a cube, b square 1 plus b cube, c square 1 plus c cube. Now there comes the concept addition of determinants. Do you remember something like that we have seen in this lecture, seen in this one shot? Let's apply that part. So this particular part which we are given in the question, I'm writing as a sum of two determinants, which we can do. I hope you must have remembered. I'll keep these two columns, first and second, as it is, but I'll break this third column. I hope you know how to do that. So first column, I'll be writing, first determinant, I'll be writing as a square, b square, and then c square, right? Third column I'm yet to write, so I'll write it later on. But as of now, I'm writing the other part here. So again, first two columns, a square, then b square, and then you have c square. Now what do we do? We are splitting the third column. How? 1 1 1 I'll fetch from here, so I'll give it to the first determinant, and the other one is a cube, b cube, c cube. I'll give it to the second determinant. Are you comfortable with this part? And we are told that this value right here is 0. So this is what we are told over here. I hope this part is very well understood by you all. Now what do we do next? I'll do a very simple formula here. I'll apply a very simple formula here. I will first of all do some column operations here on this first determinant. What are those column operations, students? First operation is I will interchange these two columns. So what will happen when you do that? I will have 1 1 1 1 in the first column and I'll have ABC in the second column. Then I'll perform one more operation. Now I hope you are able to imagine. I have ABC here after that operation. So I will interchange these two columns, column 2 and column 3. Well, by doing that, I'll have ABC here and A square, B square, C square here. Why am I doing it? I'm trying to convert that into this kind of format. I don't know why as of now, but I'm trying to do it. Maybe I'll get something from here and then I may be able to find the value of ABC. I hope you're getting this intent that why are we doing it possibly, right? Now, so here I'm doing two column operations. I'm interchanging columns twice and if I'm doing it twice, which means even number of times, which means negative will make it positive. So no sign change will happen. I hope you're realizing why, because two times we are doing this interchanging of columns, and that's why I'll straight away write the desired results. What I am doing here is I am performing two column operations. First of all, I am here interchanging column 1 with column 3. So first of all, we are interchanging column 1 with column 3. And then after that, once that interchanging happens, I'll interchange column 2 with column 3. I hope you must have understood this. Column 1 with column 3 will give me 1 1 1 here. And then A, B, C and A square, B square, C square when interchanged will give me 1 1 1 A, B, C and A square, B square, C square like this. So this kind of a result will be attained by this, and two times this column interchanging is happening, hence sign won't change. So what will happen to this determinant? I am writing that part here. So I'll be having 1 1 1 and then A, B, C and then A square, B square and C square like that, right? Plus, what do we have next here? I hope most of you must notice that from first row, I can take A common. From second row, B can be taken common. And from third row, C can be taken common. So from first row, if I'm taking A common, then I'll be left with 1A square. From second row, 1B square. From third row, 1C square. What did you get? You got something really interesting. What is that interesting part here, students? What is that interesting part? From first row, I took A common. From second row, we took B common. And from the third row, we took C common. And when you did that, you again got the same determinant, 1A square, 1B square, and 1C square, right? And this is what we are given as 0. Now going ahead further, most of you must have noticed the answer, and if you haven't, let me go to the next step. I hope you can see this determinant here will have a value, plus something into this determinant will have a value, but these determinants are identical, which means there is a fixed value here, plus something into that same values here. So I can take this determinant common. I hope you're getting it. So when you take this determinant common, what are you left with? 1A square, then 1B square, then 1C square, right? Whole times this determinant times. What do we have? What are we left with? So we are now left with 1 here and ABC here. So with this, I am left with 1 plus ABC is equal to 0. Now we know the product of two factors is found to be 0, which means either this will be 0 or this will be 0. Can it be 0? As we have already discussed that these three factors are non-coplanar, which means this will not be 0. And if this cannot be 0, the other factor has to be 0. What is the other factor we are dealing with? The other factor is 1 plus ABC, that should be 0. And if 1 plus ABC is 0, can I conclude that ABC should be minus 1? And that's exactly what we were asked. What should be the value of ABC? And it should be minus 1. Did you understand? How are we using these properties? How are we using these expansions? How should you learn them? How can these properties be used? And how are they mingling or merging two different chapters together? to club the concepts. So that's how determinant plays a crucial role in almost all the chapters. They have their own applications with determinants. With that, if I proceed further, there comes the next property. What is that next property? A very important one, a very significant one. Do you remember in quadratic equations, we have discussed the factor theorem? What was it? If in f of x, if I am replacing x by alpha and f of alpha is found to be 0, we say that x minus alpha is a factor of f of x. Because f of x, when x is replaced by alpha, generates 0, which means f of alpha is 0. That means x minus alpha can perfectly divide f of x. That's exactly what happens with the determinants as well. For example, let's say if there is a determinant delta and if it becomes 0 on putting x is equal to alpha, then we'll say that delta is also having a factor x minus alpha, or x minus alpha is a factor of delta. How? Let's learn it with an example. Let's say if I were to give you a determinant x square x cube 5 9 16 248, sorry 248, yes. Now if I put x is equal to 2, if I put x is equal to 2, what do I get? 2, 2 square, 2 cube. What does it mean? 2, 4, 8. Can you see something here? 2, 4, 8 in the first column, 2, 4, 8 in the third column, which means first and third column are identical. And if two columns are identical, can I say the determinant should be 0? Yes, exactly. So if either two columns or two rows are identical, we know by the property that the determinant is 0. So yes, by replacing x by 2 here, I am clearly getting that the two columns are becoming identical, which means the determinant is becoming 0. And if the determinant is becoming 0 when x is replaced by 2, then I will say that x minus 2 will be one of the factors of delta. Will you remember this as a property? This property has its own applications while factorizing these questions. See, when we did this, when we learnt these circular, circular determinants, that factorization method actually helps you a lot in finding such factors here. When you replace a by b here, it becomes 0. When you replace b by c here, it becomes 0. So you can conclude a minus b, b minus c, c minus a will be the factors. So such factors can easily be found by using this factor method. That's exactly what I'm trying to give you with this particular part. Not just that, along with this, what you can also conclude is that when you replace x by 0, 0, 0, 0. So if any row or any column has all the elements 0, the value of the determinant will be 0. Why? Because that row or that column which has all the elements 0 into its cofactors, whatever they could be, will be generating 0 as the value of the determinant. I hope you are technically understanding this. So in that case, if I replace x by 0 here, the determinant will be 0. Well, in that case, x minus 0 will also be one of the factors, which means this will have at least two factors. It can have more than two factors, which I haven't explored so far, but two factors are directly visible, which are x and x minus 2, which means this determinant, when expanded, will perfectly be divisible by x and x minus 2. Did you get that part? How interesting it is? So yes, determinants have their own factor theorem as well in their own sense, but I hope you're understanding why and how. The logical explanation is also understood by you all. Well, now let's talk about multiplication of determinants. What we will study when we study the chapter matrices, there we'll talk about multiplication of matrices. We'll talk about that, don't worry about that. But multiplication of determinants also exist. Multiplication of determinants can be done by row, row by column, column by row, column by column, whatever sense you wish to do it. And with whichever method you do, the value of the determinant remains intact. It does not change. What I'm trying to make you understand is, first of all, what you need to understand is the order of the determinant must remain same. For example, let's say you have this determinant. Let's say there is this determinant A, which is A, B, C, D, and there is this determinant B, which is E, F, G, H, and you are asked to multiply them. So there are multiple ways of multiplying them. See, one of the ways is you find their products, right? You expand it, that you find the value of determinant A, and then you find the value of determinant of B, and then you multiply them. That is also fine. Or what you can also do is, you find, let's say I replace them by delta 1 and delta 2 so that you don't get confused. This here is delta 1 and this here is delta 2. So here it is delta 1, let's say, and here it is delta 2. So if I'm finding delta 1 by expansion, of course, I'll find delta 1. And if I'm finding delta 2 by expansion, I can do that. And then I take their product, that is fine. But there is one more method, which is I take their product. Now, how do you multiply determinants? So I'm explaining one of the methods. The rest of the methods can be understood by you very easily. So I am explaining row by row determinants multiplication. Well, similarly, row by column can be done, column by row can be done, and column by column can also be done. Through all these four methods, you will get the same value of the determinant. That's what I'm saying as a fact. Remember it. So I'll show you, demonstrate you row by row determinants multiplication. How does that happen? I'll choose first row of delta 1. I'm writing the product of delta 1 and delta 2. What will that be in terms of determinants? That's what I'm going to write. So first row of delta 1 and first row of delta 2. So corresponding elements, A into E will take place. So that will be AE plus B into F will take place. That will be BF. Then this first row I'll multiply with the second row here. So that will be A into G here plus B into H here. I hope you're getting it. Now what will I do? I'll take the second row here. Now this CD will multiply with EF, which will give me CE plus DF. Similarly, this CD will get multiplied with GH here. So that will be CG plus DH. So before starting, multiplying the determinants, you need to ensure that they have the same order. And this multiplication process can be done either row by row, row by column, column by column, or column by row. I hope you are understanding it. Sir, how can you do row by column? So I choose this row and this column, then this row and this column, then this row, this column, then this row and this column. In that case also, when you expand the determinant, you'll get the same value. I hope you're understanding that there can be 4 types of multiplications possible on determinants. Whichever method you choose, you'll get the same result. That's what I'm constantly emphasizing upon. My motive here is that questions are not asked on the multiplication of determinants. Rather, they give you something like this and they expect you to create something like this. That they give you the product and then they ask you to break it. So they basically try to assess your understanding of factorizing the determinants. Now that is even more interesting. There you need more intuition, there you need more intelligence, there you need more awareness, there you need to be more observant. How? Let's have a look at that. So I hope matrix multiplication is understood by you all, that if I am having a 3 by 3 matrix, 2 matrices delta 1 and delta 2, and if I want to find their product, it can be found in 4 ways: row by row, row by column, column by column, or column by row. For example, if I wish to proceed with the method row by row, let's say row by column. So how do I do that? I choose this first row A1, B1, C1, and then I choose this first column alpha 1, alpha 2, alpha 3, corresponding elements, product and sum will be done. That's where you write the first element of their product. Then this first row with second column, then first row with third column. 3 elements of the first row are written. Then second row, first column, second row, second column, second row, third column. 3 elements of the second row are written. Then third row, first column, third row, second column, and then third row, third column. So that's how row into column. Similarly, column into column, column into row, all of them will yield the same result. The determinant's value will remain unchanged. That's what I'm trying to make you understand. Now, if this part is understood by you all, let me explain it more clearly with this example, that you need to find the value here. Although they are asking in terms of prove that this is 0. Or sometimes, let's say in the examination, you're given this determinant and you're asked to write its value. How will you do that? If I know the multiplication of determinants, I can write it in a more effective and intuitive manner. How? Let's learn that. See, can I represent this product, this expression, as a product of 2 determinants? This determinant given me over here, can that determinant be written as a product of 2 determinants? There you need some intuition, there you need some intelligence, there some kind of intelligence is expected out of you. Now, how is that intelligence applied? Let us learn that. See, I am seeing A1, A1, A1. Pay attention to it. I am seeing A2, A2, A2. Then I am seeing A3, A3, A3. But in the first row with A1, I had alpha 1, then alpha 2, then alpha 3. then alpha 1, alpha 2, alpha 3, then again alpha 1, alpha 2, alpha 3. So let's try and get this result. How can we get that? Okay, so I am writing here, see, A1, 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 right? So let's say if I write A1, then A2, then A2, and then 0. And there I'm writing alpha 1, alpha 2, and then 0. Let us see what do we get. Let us see what do we get. I'll be performing row into column. So the determinants multiplication I'll be doing is, I'll be doing that row into column. So I'll take the row and multiply it with the column. That's what I'll do. So that's the process I'll follow. And I'm seeing that whether this yields the result which I'm expecting or not. So what I've done here is, I am multiplying, please understand, there is a catch that this will not yield the desired result, but let me show it to you whether it yields or not. So row into column. So here, please pay attention, A1 into alpha 1, I have gotten the result. But next when I do A2 into alpha 2, that is not what I want. I have wanted B1 into beta 1. Well, that's not a difficult task. All I need to do is simply remove this A2 and alpha 2 by something else. What is that? I want B1 into beta 1. So I'll write a B1 here and I'll write a beta 1 here, and then let's say I write a 0 here. So what do I get now? Let's say we are able to make it. How? A1 into alpha 1, yes. B1 into beta 1, yes. Plus 0 into 0, yes, we are able to get this. Okay, that's great, that's brilliant. Now, what is next? Sir, in the second entry here, I want A1, alpha 2, B1, beta 2. So now I want alpha 2 and beta 2 with A1 and B1. Can we get that? Yes. If I have alpha 2 and beta 2 and 0 here, I hope you can see A1 alpha 2. I hope you can see it. B1 beta 2, I hope you can see here. So I could generate A1 alpha 2 and B1 beta 2 with this row into this second column. Did you get that part? Now, sir, if we are on the right track, I think the symmetry must stand and I should go ahead with that logic. So the next requirement says A1 alpha 3 and B1 beta 3. So A1 into alpha 3 plus B1 into beta 3. I think that works. Yes. And plus 0 into 0. So that I think is working pretty well. But let us verify that one of the factors as a determinant we have already concluded or drawn completely. Does it match with the other parts as well? Are we able to generate the other entries as well? For example, now I want A2 alpha 1 plus B2 beta 1. For that, do I not need to write here A2, B2 and 0? Because when you do that, A2 alpha 1, B2 beta 1 and 0 into 0. I think we are able to generate this as a result. So I think we are going great. Let us verify it further. A2 alpha 2 plus B2 beta 2 plus 0. I think we are able to generate this as well. Similarly, A2 alpha 3 plus B2 beta 3 plus 0. So yes, we are able to generate that result as well. On the basis of this, can I predict the third row here? I think I can. A3, B3 is what I am looking at. So here I'm writing it as A3, B3 and 0. Once you write that, see, A3 alpha 1, B3 beta 1 is what I need. A3 alpha 1 plus B3 beta 1 plus 0. A3 alpha 2 plus B3 beta 2, I think we have received here. And then A3 alpha 3 plus B3 beta 3 plus 0. I think we are attaining that as well. So yes, this determinant which was given in the form of product of two determinants, we are able to write the two factors of those two determinants. We are basically able to write those two factors, which are the two determinants of this product form. I hope you are getting this part very clearly. Now, sir, how are you able to prove this, that this is 0? I think most of you must have already noticed that, sir, if a determinant has all the entries of either any column or any row as 0, then the value of that determinant is 0. So here in this first determinant, this has all the entries of the third column are 0, which means this should be 0, and 0 into anything is 0. Well, anyways, the second determinant has also the third row as 0, which means this determinant also has a value 0, which means the value of the determinant will be 0. Did you notice or see or understand that without even expanding, without using much logic, if you were aware of the product of the determinants, you could break it into two factors, and thereby looking at these two factors by observing the properties of the determinants, you could conclude the answers within seconds. Are you realizing how important these properties are? If learnt very well, these questions can be done so easily. Did you get that part, students? If that part is understood, let us move ahead. Let us proceed further where we understand system of linear equations. I'll begin our discussion with this particular thought that if I'm given two straight lines in 2D, then there are three possibilities there. Which are those three possibilities? Let us first of all understand that. I hope whenever you're given two straight lines, the chances are that they may intersect. So when they intersect, we say that there is a unique solution, which means there is a point, a single point, which satisfies both of the lines. Well, the other possibility could be that these two lines are parallel. When these two lines are parallel, we say that they don't intersect. And when they don't intersect, that means they don't have any solution because there is no common point which satisfies both of the equations. Well, there arises third possibility as well, when the lines overlap, when the lines coincide, when both of the lines lie above or on each other, when they coincide. Well, basically they represent the same straight line, but the equation is given as a multiple of the original equation. So in these three cases, what you need to understand is that this is the case where you had the unique solution. This is the case when you have no solution, and this is the case where you have infinite solutions. Why? Because there are infinite points which are satisfying both of the equations simultaneously, because both of the equations are representing the same straight line, which means all the points lying on this line will be satisfying both of the lines, which means in this case we are having infinite solutions. Well, why did we discuss all this? Why are we having a discussion all this? Because this discussion will help you in understanding the system of linear equations, which is understood in a more detailed format with the help of Cramer's rule. First of all, let's have a look at this. When do you say that a set of equations is said to be consistent equations? What does it mean? First of all, you need to understand, let's say I have a definite and a unique solution. As we have already discussed, if we are having two straight lines which are intersecting at one single point, that means they have a unique solution. When do we have a unique solution, students? I hope you all must have studied that whenever you are given two straight lines, for example, one of the straight lines is a1x plus b1y plus c1 is equal to 0, and the other straight line is a2x plus b2y plus c2 is equal to 0, we say that this system of equations, basically two straight lines are there, and this system of equations will represent a unique solution if. When does it represent a unique solution, students? I hope you remember, unique solution is represented by this system of equations when a1 upon a2 is not equal to b1 upon b2. That means these two lines are neither parallel nor coinciding. They are intersecting, and when these lines are intersecting, then we say that on coordinate plane they will intersect at one unique point, and that will be the solution. Well, in that case we say that this system of equations is consistent and it shows a unique solution. That's exactly what I'm trying to make you understand here. They have taken an example, x plus y is equal to 2, x minus y is equal to 6, because here when you solve them, when you find the solution, you get a unique solution, x is equal to 4 and y is equals to minus 2. That is a unique solution, and it proves that these are two intersecting lines, which can be assessed by this method as well, that 1 upon 1 is not equal to 1 upon minus 1, because 1 is not equal to minus 1. And that's how you could have also said that yes, these two lines are intersecting ones. So did you all first of all understand that whenever you are given system of linear equations, if you are asked to check whether it has these equations are consistent equations or not, or whether they have a unique solution or not, then this is the simplest method you can apply or think of. But this is not exactly what we'll keep doing. We'll discuss what is needed to be done. But apart from this, there is something more. What is that? Let us explore all the possibilities first of all. The next possibility is, what if I am told that the equations are inconsistent? Now, what does it mean? It means that there is no solution. It means the lines are parallel. I hope you must have remembered the case that if two lines are parallel, that means they won't intersect anywhere. And if they are not intersecting anywhere, which means there will be no solution because they don't intersect anywhere. There is no common point which is satisfying both of the equations. Well, in that case, we say that this system of equations is first of all inconsistent and it has no solution. As we have already discussed that if you are given two straight lines which are a1x plus b1y plus c1 and a2x plus b2y plus c2 is equal to 0, and it represents an inconsistent system of equations, which means it represents a pair of straight lines, which means it represents that these two straight lines will not have any solution at all. Well, in that case, this would be true, which means a1 upon a2, b1 upon b2 will be equal. That signifies that they have the same slope. These two lines have the same coefficients of x and y, which means if the coefficients are proportional, these two lines must be parallel. But when c1 and c2 are not proportional, as a1 and a2 and b1 and b2 are, well, in that case, these two lines are not coincident. These two lines are not overlapping. These two lines are actually parallel, and when these two lines are parallel, it says that they don't have any solution. So in that case, for example, here x upon x and 2x, y and 2y, which means 1 upon 2, 1 upon 2, but when you look at these constant terms, they are 2 upon 5, right? So yes, 1 by 2 is equal to 1 by 2, but that proportion is not equal to 2 by 5, and hence we say that this system of equations is representing parallel straight lines, a pair of parallel straight lines, which means this does not give you any solution, and hence we call it an inconsistent equations, a pair of inconsistent equations. Did you get that part, students? Along with this, what you need to understand is that there is one more case which you all should remember is dependent equations. Now, what does it mean, dependent equations? It means infinite solutions when you have identical lines. Now, what do you mean by identical lines? Look at this particular part. Initially, you had x plus 2y is equal to 3. What if I multiply this equation by 2 on both these sides? The equation wouldn't change, but it may look different. How? If I'm multiplying this equation by 2 on both these sides, it will become 2x plus 4y is equal to 6. Right, students? Well, that makes us understand that here both of the lines are representing the same straight line. These are not two different equations, rather they are representing the same straight line, but the equation is written a little differently. How do you observe it? The observation remains very simple: 1 by 2, then 1 by 2, then 1 by 2. If you take their ratios of the coefficients, 1 by 2, 2 by 4 and 3 by 6, they have the same ratio 1 by 2. So if you are having a1 upon a2, b1 upon b2 and c1 upon c2 to be same, which means these two equations are not two different straight lines. They are representing the same straight line, and if it is representing the same straight line, which means the lines are overlapping, they are lying on each other. So both of the lines are same line, which means they are not two different lines, which means there are not unique solution. There is no solution, but there are infinite solutions, because all the points lying on that line will satisfy the line, and that means infinite points will lie on that line. So it will have infinite solutions. Did you get that part? So I hope this part is also very well understood by you all, where we say that this is a dependent equations set. I hope these three cases are very well understood by you. With these three cases, we are creating that foundation where we'll start understanding Cramer's rule. Because now, when you come to Cramer's rule, it has suggested that no matter how many number of variables you have, you can actually solve those equations. All you need to do is, let's say if you have three variables, let's say x, y, and z. So to find solutions, you need to have minimum three equations in x, y, and z. That is what the Cramer's rule says. How do you apply it? How should we use it? How can we, get results from it? That is what we'll discuss here. But first of all, let us understand in the context of three variables that how do we apply the Cramer's rule? Because your syllabus also restricts you to this particular rule up to this stage only, where you deal with three variables in three equations. How do we do that? Let's say I'm given three equations, linear equations. So the power is 1. And there are three variables: a1x, b1y, c1z is equal to d1, A2x, B2y, C2z is equal to D2, A3x plus B3y plus C3z is equal to D3. So these are the three equations and I'm supposed to solve them. One of the methods is use substitution elimination. You will get rid of one variable, then try to solve them with two variables, then again use either substitution or elimination, and then somehow you will find one of the variables, then substituting it to the other, then you'll get another variable, and then substituting those two values, you will get another variable. That's again a cumbersome process that takes time, that needs some intelligence. Of course, that is advised to all the students, but if you're stuck, if you don't know much, if you don't want to use much brain, if you just want to apply things in the formula, you have a formula. Give the values to this formula. It will give you all the variables. It will give you the values of all the variables. It will give you the solution. It will give you that what could be the possible values of x, y, and z, which will satisfy this particular linear equations group. How? Have a look at that. Please understand, here you need to define certain things. What are those certain things? First of all, I'll deal with the coefficients of x, y, and z. What are they, students? They are A1, A2, A3, B1, B2, B3, and C1, C2, C3. So first of all, create a determinant or find the value of the determinant, which is the coefficients, which is created by the coefficients of x, y, and z. So A1, A2, A3, B1, B2, B3, and C1, C2, C3. This is what we take and we call it delta. Conventionally, traditionally, we call it delta. So first of all, you need to find delta. Now, what is next? Now I'll find three things. Delta 1, some books call it delta x, then delta 2, some people call it delta y, and delta 3, some may call it delta z. Now, what do you do when you try to find delta 1, delta 2, delta 3? The job is really simple, students. Here, what was the coefficient of x? A1, A2, A3. So that column or that row, whichever contains A1, A2, A3, that gets substituted by D1, D2, D3 to find the value of either delta 1 or delta x, whatever you're willing to call it. Let's say I'm willing to find delta y, or let's call it delta 2. So to find delta 2, the coefficients of y, b1, b2, b3 are replaced by the constant terms d1, d2, d3. So that's how you define delta 2. So a1, a2, a3, c1, c2, c3 remain intact. They don't change. But b1, b2, b3 is replaced by d1, d2, d3. Well, how do you find delta z? Can you help me with that? I hope you know how to do it. Delta 3 or delta z will be simply nothing. But first of all, these two rows or columns, A1, A2, A3, B1, B2, B3 will remain intact. But with this C1, C2, C3, you will replace it by D1, D2, D3. So to find delta z or delta 3, the coefficients of z, which were C1, C2, C3, are replaced by the constant terms D1, D2, D3. So what do you have now? Delta 1, delta 2, delta 3. How did we find that? Delta created with the coefficients of x, y, and z. Delta 1, delta 2, delta 3 are the, when you substitute the coefficients of x, y, and z respectively by constant terms. That's how you get delta 1, delta 2, and delta 3 respectively. Did you get this part, students? So once you have cracked delta 1, delta 2, delta 3, now I hope you know how to solve a determinant. So you need to find 4 determinants. Delta 1, delta 2, delta 3. Once you have found all these values, find the value of delta 1 upon delta. That will give you x. Find the value of delta 2 upon delta. That will give you y. And find the value of delta 3 upon delta. That will give you z. All I'm trying to make you understand is a very simple phenomena that by using determinants, you can solve system of linear equations. The proof of this is beyond your syllabus, first of all, and that is what we may not be able to discuss in this one shot. So I'm giving you the direct result. How should you apply it? What is needed to be done? And I'll be hoping that you should use this result while solving system of linear equations. Although one of the methods is always there with you, that you solve these 3 equations which you are taught how to. That is not a huge task which you are not able to or which you are not capable of. So always remember, Cramer's rule is also there to assist you in finding or solving linear equations in different number of variables. Along with this, this is not exactly what IIT JEE is obsessed with. This is not exactly what IIT JEE asks. from determinants, they know that this particular set of linear equations or a triplet of linear equations can be solved even without determinants. So how do they force you apply the concepts of determinants, in this sort of questions? Well, that's exactly what we'll explore now. So let us move further and understand what all we'll be discussing further. But before I move ahead, I hope I have your confirmation and validation that this is something you have understood very clearly. Four things: delta, delta 1, delta 2, delta 3, and then delta 1 upon delta x, delta 2 upon delta y, and delta 3 upon delta will give you the value of z. Now, proceeding ahead, students, what do we have next? Now, here, please understand, this is what JEE is obsessed with. This is what JEE asks you. JEE does not deal with this x and y and z. They don't ask much about x, y, and z. Rather, they want to assess or know whether you know this or not. So this part is a very crucial part, which is asked more by JEE. Now, how do they ask it? Let us explore this concept first, and then we'll explore questions based on it. What is there given to us? See, first of all, while exploring delta, delta 1, delta 2, delta 3, these four values will give you a lot of clarity about the equations being consistent or inconsistent. The equations having a unique solution, no solution, or infinite solutions. That's exactly what can be discovered or figured out with the help of the values of delta, delta 1, delta 2, and delta 3. How? Let's have a look at that. See, if I am told that delta is not equal to 0, let's say by some means I wrote this determinant A1, B1, C1, A2, B2, C2, and A3, B3, C3. This is the determinant of the coefficients of x, y, and z. And I could find this determinant is not equal to 0. Then I'll say without any hesitation that the system of these equations is consistent, and it means it will have a unique solution. Whenever you get the value of delta as non-zero, so whenever you have this delta as non-zero, I hope you're realizing, whenever you get this delta as non-zero, then you can always conclude that this system of equations will have a unique solution and it will be consistent. We will have more clarity on this when we discuss the chapter matrices, but right now I am emphasizing you to remember these as results directly, without delving much into the details. I hope this part is very well understood by you all. When you go to the next part, which says that if delta is 0, okay, before discussing this part, let me come to this part. If all four, delta, delta 1, delta 2, delta 3, all of them are 0. So delta, delta 1, delta 2, delta 3, if all of them are 0, then equations will have infinite number of solutions. Then equations will have infinite number of solutions, which means equations are consistent. Again, I'll come back to this part here. When you have, what I am trying to make you understand is that this exactly does not look like this. This exactly looks like this. X into delta is equal to delta 1, y into delta is equal to delta 2, and z into delta is equal to delta 3. So when you have delta and delta 1, delta 2, delta 3, all of them to be 0. So yes, 0 into anything will be 0, 0 into anything will be 0, and 0 into anything will be 0. So no matter what value of x, y, and z is brought into picture, you will have this particular part getting satisfied. What does it imply? What does it mean? It simply means that whenever you have delta, delta 1, delta 2, delta 3, 0, that means the equations have infinite number of solutions. And in that case also, you say that the system of equations is consistent. So whenever you say that the system of equations is consistent, then you come up with a conclusion that either it will have a unique solution or it will have infinite solution. I'm really sorry, it will have infinite solutions. But whenever you wish to say that the system of equations is inconsistent, then it simply means that it will have no solution. Now, what do you mean by a system of equations having no solution? What does it mean? Let's explore that part. Now, please understand, let's say you get delta to be 0. First of all, our modus operandi will ask us to find delta. There are two cases. What are those two cases? You will have either delta to be 0 or delta to be not 0. So in the case of unique solution, you will have delta to be not equal to 0. But in case of infinite solutions, you will have delta equal to 0. And in case of no solutions also, you will have delta to be 0. But what is the difference between no solutions and infinite solutions? Whenever you have infinite solutions, when in that case, delta 1, delta 2 and delta 3 will also be 0. But when you say that even if at least one of them is non-zero, one of delta 1, delta 2, delta 3. So if I see that at least one of delta 1, delta 2, delta 3 is non-zero, then we say that the system of equations is inconsistent. It is not following the consistency. We are not finding the equations to be in sync. And there we say that yes, no solution exists. There is no particular value of xyz which will satisfy our requirement. What I'm trying to make you understand is, let us understand this with a better example. Please understand. Let's say, to make us understand, let's say that delta is 0, delta 1 is 0, delta 3 is 0, but delta 2 is not 0. So what we know is delta 0. So if delta is 0 and delta 1 is 0, 0 is equal to 0, this is consistent. If delta is 0 and delta 3 is 0, so 0 is equal to 0, this is also following our consistency. But if delta is 0, but delta 2 is not 0, then 0 is not equal to non-zero. But here, I am finding that relation that 0 is equal to non-zero, which is a violation of mathematics or the laws of mathematics or the rules of the mathematics. And that's where we say that here, the case of system of equations having no solution arises, which means in this case you will say that the system of equations is inconsistent. So what does it mean? It simply means or concludes that whenever you have delta is equal to 0 and along with this at least. Now what does at least means? Either all of them could be non-zero or two of them could be non-zero, or at least or exactly one of them will be non-zero. Well, when at least delta 1, delta 2 and delta 3 is not 0, in that case you say that the system of equations has no solutions. You need to remember this particular part. This should be your cheat sheet while dealing with questions based on Cramer's rule. So always remember, first of all, system of equations will be given to you, usually 3 as per your syllabus. Then what happens? Then you basically deal with 3 cases: unique solution, no solution, infinite solutions. Unique and infinite are part of equations being consistent, and no solutions is a part of equations being inconsistent. Second thing which you need to learn is whenever there is unique solution, delta will be non-zero. That's it, and then your job is done. Nothing needs to be investigated further. But when it comes to dealing with either infinite solutions or no solutions, you need to deal with the values of delta 1, delta 2, delta 3 as well. So whenever you are claiming that this system of equations has infinite solutions, then you say that delta 1, delta 2, delta 3 should also be 0. But whenever you are claiming that this system of equations have no solution, well, in that case, at least one of delta 1, delta 2, delta 3 will be non-zero, whereas delta was 0. I hope there is no confusion on it. You have understood in a very detailed format with utmost clarity, and I hope with that we can move to the question where we explore it with more clarity. So here we are given a question, of course asked by JEE Mains in 2025, a very good question, and it will give you complete clarity about the concept which we have discussed as of now. What is it? We are told that this system of equations have infinitely many solutions. So this system of equations have infinitely many solutions. Well, that's okay. That's brilliant. Then the number of solutions of this system if x, y, z are integer. Okay. So this part I'll explore later. I'm not talking about this part. Let me come to this part first. When somebody says that this system of equations has infinitely many solutions, can you help me with this part? When somebody says that these 3 equations, their system has an infinite solutions, what does it mean? Can we say that delta 1, delta 2 and delta 3, all of them will be 0? But before I put all of them to be 0, how many variables am I dealing with? I'm dealing with lambda and mu. So I think I need to find two variables. And to find two variables, I think two equations will be sufficient. So I'll be dealing with two things. Let's deal with delta first. And then let's deal with delta 1. Because delta, when put equal to 0, might give us with the value of lambda. And when you put delta 1 is equal to 0, that may give us the value of the mu. So these two things I need to work upon, right? So let us write this part. So delta, if I were to write the value of delta as per our understanding should be 1, 5 minus 1, the coefficients I'm writing here. So delta will be 1, 5 minus 1. I hope you can see it here. Then you have 4, 3 minus 3. Okay, so you have 4, 3 and minus 3. Then what do we have next? 24, 1 and lambda. So this is 24, 1 and lambda. This is what we need to work upon. And we know that this system of equations have infinite solutions, which means delta should be 0. Well, in that case, delta is what I need to work upon. So let me use the Sarrus rule. What does Sarrus rule say? Sarrus rule says that 1, 5 minus 1 and then 4, 3 minus 3 is what I'll write here. And then I'll expand it. As per my understanding, the expansion will be 1 into 3 into lambda. That will be 3 lambda. Then 4 into 1 into minus 1. That will be minus 4. Then 24 into 5 into 3. So I think 24 into 5. 24 into 5 is 24 into 10 by 2, which is 120. And 120 into 3. So 120 into 3 is, I think, 360. Well, it should be minus 360. That is what we need to be aware of. So that is the first part we have explored so far. Let's talk about the next part, students. What is the next part here? I'll talk about the next part in this manner, that this particular part, 24, 3 and minus 1. So 24 into 3 is, I think, 72. So it should be minus 72 here. So I'm writing a minus 72 here. Then we have, I think I have mistakenly took something wrong. Yes, that's right. 24 into 3 into minus 1, that's minus 72. Then minus 3 into 1 into 1, it should be minus 3. Then what do we have next? Then we have lambda into 5 into 4. So it should be 20 lambda, which I'm writing here, 20 lambda. And this determinant should be equal to 0, because we were told that this system of equations having a infinite solutions. So when I proceed further with this particular part, how do I deal with this? See, I'm trying to find lambda from here. So 3 lambda minus 364. I think this is what I'll get from here. And then minus, what do I get from here? I think minus 72 minus 3, that's minus 75. So it should be plus 75 and minus 20 lambda should be equal to 0. Right, students? I hope there is no confusion on it. Now, when you proceed further, what do we get next? I think when I proceed further, I should deal with this 364 and 75. So I need to subtract 375 from 64. So first of all, let me subtract 64 from 364. That will be 300. But 75 and 64, 64 plus 6 and 5, 11 more are to be subtracted. So 300 minus 11 will give me 289. Yes. So it should be minus 289, right? I'm pushing that minus 289 to the other side. So that will become plus 289. So here, this is the difference, which is 289. And 3 minus 20 is 17 lambda. So here I'll have minus 17 lambda. We all know that 289 is the square of 17. So from here, I could crack the value of lambda. Which is found to be minus 17. So first of all, we have found the value of lambda, which if needed, I'll use as minus 17. So that's our first conclusion, right? Now, let's talk about mu. I hope there is no confusion on it. Let's talk about mu now. So to find mu, let's write delta 1. I think with delta 1, I may be able to find the value of mu. So let's write delta 1. What do we do in delta 1? The coefficients of x are replaced by the constant terms. That is how you find the value of delta 1. So what are the coefficients of x? 1, 4, 24. They will be replaced by 1, 7 and mu. So here, I'll be writing 1, 7 and mu. What am I writing here? I'm writing the value of delta 1. Then the two coefficients 5 minus 1, 3 minus 3, 1 and lambda, they'll remain same. So 5 and minus 1, first of all, I'll write. So 5 and minus 1. Then what do we have next? 3 and minus 3. Okay. So 3 and minus 3. Then what do we have next, students? 1 and lambda. Okay, so 1 remains 1, but do we know the value of lambda? Yes, we have already cracked it. That is minus 17. So this is what we have as delta 2, right? Sorry, delta 1. Now again, can I expand delta 1 with the help of Sarrus rule, as we have already learned? So what does Sarrus rule say? I'll write 1, 5, minus 1 here, right? And then I'll write 7, 3 and minus 3 here. Now, again, when Sarrus rule is applied, what do we get? This delta 1 should also be equal to 0, because we were already told that this system of equations contain an infinite solution set, right? So it means this delta 1 should also be 0. So here 1 into 3 into 17. So that is minus 51, I believe. So here I'll be getting minus 51 first. Then you have 7 into 1 into minus 1, that's minus 7. So that is minus 7 from here. And then you have mu into 5 into minus 3, that's minus 15 mu, which is what we are getting from here. So this is the first part. What about the second part? Minus 1 into 3 into mu, that I think is minus 3 mu. Okay, so we are going great. Then you have minus 3 into 1 into 1, which should be minus 3. So this should be minus 3. Then what do we have next? 17 into 5 into 7. So this is what I need to have. What do I need to have? 17 into 5 into 7, right? So I'll do this multiplication here. What I need to do is 17 into 35. I hope this is what I need. Yes, right, with the negative sign, of course. So this is what I'll do here. See, I think 17 into 5 is 85. So I'll be having 5 here. And then, of course, 8 is the carry, right? So 17 into 3. 17 into 3 is 51. And 51 plus 8, right? The carry was 8. So 51 plus 8 should be 59. Correct me if I'm wrong. I hope we are doing the calculation correctly. With such part, you should be more cautious, because all the efforts you have done will go in vain if you do any silly error here. So be very cautious and alert when it comes to calculation. Don't rush. Have your own patience. Have your own cool, calm, composed mindset, and then do it. Now, minus 17 into 35. So 17 into 5 is 85. I think that gives us the carry 8. We write 5 here. 17 into 3 is 51. Plus 9 is, plus 8 is 59. So this should be minus 595. And that is minus, yes. So minus 595 is what I'll write here. And we know that this should also be equal to 0. So from here, when I explore this particular part, minus 51 minus 7 is minus 58. And there you have minus 15 mu. And from here, you have minus 595 minus 3, which is minus 598, I believe. But minus minus will make it plus. So this is 598. Yes. And then plus 3 mu is equal to 0. Right. Now, what do I get next? I think we have the conclusion now. First of all, minus 15 mu plus 3 mu will give us minus 12 mu. And there you have 598 minus 58. So I think 590 minus 50 should be, I think, 540. Yes. So it should be 540, but when it goes to the other side, it should be minus 540. I hope we are going great. Yes. Right. Now, when you divide 540 by 12, what do you get? I think the result is very simple. So 12 into 4 is 48, because 12 into 5 is 60. So first of all, this minus gets cancelled by this minus. So 12 into 4 is 48. And 54 minus 48 is 6. That is 60. So 12 into 5 is 60, which gives us the value of mu as 45. So we are able to crack the value of mu as well. So now the value of mu is found to be 45. These are the two values we have cracked. Now, our job is half done. Why? Because the remaining question is little more trickier what you might have assumed, because with this they have clubbed inequalities in equations. How? Let's solve a question on inequations now to complete it. What does it say? That the number of solutions of this system, if x, y, z are integers and they satisfy this particular conditions. Okay, so first of all, let me write these three equations again. What are these three equations? These three equations are x plus 5y minus z is equal to 1. That's our first equation. Then you have 4x plus 3y, right, minus 3z is equal to 7. That's your second equation. Okay, nothing related to lambda and mu was involved. Then you have Then you have 24x plus y. Then lambda z means minus 17z is equal to mu, which is 45. So these are the three equations we are now dealing with, right? So these are the three equations we are now dealing with. And we need to put certain constraints that x, y, z should be integers, which I'll think of later. But x, y, z satisfy this particular condition. I'll try to find the values of x, y, z. We know that it is a system of infinite solutions. So I'll be able to express x, y, and z in terms of a different variable, because they'll be proportional. Because when there are infinite solutions, they'll have their own proportionality. So x, y, z are related and they'll have a pattern. So how are they related? Let's work on finding that. Please pay attention to it. This part is even more crucial. How? Have a look at this part. First of all, I'll try and solve these two. So when you try and solve these two, I'm multiplying this particular equation by 4. So when you multiply this particular equation by 4, or let's say minus 4, what do I get? I get minus 4x and then minus 20y, and then minus 4 makes it plus 4z is equal to minus 4, right? Here I'll keep it like this only. So it is 4x plus 3y, and then you have minus 3z is equal to what? Is equal to 7. And there you add both of these equations. So 4x are cancelled. 20y minus 3y is minus 17y. From here, 4z minus 3z leaves you with, I think, z. And there it is, I think, plus 3. So from here, I am able to write z as 3 plus 17y. So I am writing z as 3 plus 17y. That is also something I'll remember as a result. I hope this part makes complete sense, whatever I've done so far. Now, let us proceed further and let us move ahead with, finding the value of, let's say, x. So this value of z, which we have received as 3 plus 17y, can I replace it here and can I write x as well in terms of y? So let us try and do that. So from here, I am replacing z by 3 plus 17y, and let's see what is the value of x which we receive from here. So when you do that, what is the value you receive from here? Let's work on that part. Okay. So if I am replacing z by 3 plus 17y, okay. So this is x plus 5y. Then when you replace z by 3 plus 17y, it should be minus 3 and then minus 17y, which is equal to 1, I think. I hope there is no confusion on that. This part which I have received, x plus 5y, then z I have received by minus 3 minus 17y, because minus z was it, and then is equal to 1, right? From here, if I find the values of x, I think I may be able to get certain values. Okay, let's try and do it, because I think I should have put the value of z here, which I haven't, but let's see what do we get. If we don't get the desired result, I'll try to use this particular equation, which we haven't used so far, and the idea of finding lambda and mu goes in vain. But let's try and do it with the help of this. If this doesn't work, I'll go to the third equation. That's the approach I'm thinking of. So here, x plus, right, minus 17y plus 5y is basically minus 12y. That minus 12y pushed to the other side, so that becomes plus 12y, and there you have minus 3, which goes to 1, becomes or makes it plus 4. So from here, I could get the value of x as well in terms of y, which is nothing but 12y plus 4, right? So these are the certain values which we have attained so far. Now, forget this too. Now what we know is that x, y, z are integers. They are integers, okay? I'll use this result. But before I use this, do I have one more result? Yes, that x plus y plus z is a value which lies between 7 to 77. That is what the constraint which they are imposing here. So can we use that constraint? Yes, x. So I'm calling x to be 12y plus 4, which we have already explored, plus y, which I keep as it is, plus z. What is z? Z is 3 plus 17y. I hope there is no confusion on that, whatever I've written so far. And this value is said to be lying between 7 and 77. I hope no confusions on that. This value lies between 7 and 77. Now what do I get next? See, from here, if I pay more attention, then it makes it 12 plus y, which is 13y, and 13y plus 17y is 20 plus 10 is 30y. So this gives us the value 30y, right students? Well, here we have one more result, which is 4 plus 3, which is 7. So 30y plus 7 lies between 7 and 77. If I subtract 7 from all the three sides, because this is what you do with inequalities, I'll get 0 from here, I'll get 30y from here, and I'll get 70 from here. The next part says that I'm, dividing all the three sides by 30, because 30 is positive, the signs won't change. So when I'm dividing all the three sides by 30, where should I write the conclusions? Can I write the conclusions here? So I'm writing the conclusions here. I hope that doesn't bother you. So I'll be writing the conclusions here. I hope this part can be utilized as per our need here. So here we have this particular part where I'm saying that this inequation on all the three sides is being divided by 30. So the result which we receive is 0 is less than equal to y is less than equal to 70 upon 30, which means 7 upon 3. And 7 upon 3 is approximately, as per my knowledge, is 2 point something, right? 2 point something. Even 3 2 ja 6, remainder 1, so 2.3 something, right? Now, I'm not interested in its exact value. Let's stick to this particular part. So we know y has three values. Which three values? Y begins with 0. 0 is an integer, so that is perfectly fine. So y takes three values. Which three values? 0, then 1, and then 2. So y has taken three values. I hope you can see, because up to 2 I can go, but I cannot go ahead of 2 because y gets restricted with 2.3. So y cannot be 3. When y is 0, do I have x, a value of x which is integer? Yes. Do I get a value of z which is an integer? Yes. Because z and x are directly, linearly and straightforward manner dependent on y. So whenever y is an integer value, y takes an integral value, x and z, I hope you can see, will also take integral values. So here what you need to understand is, that if y is taking these three integral values only, as per the condition given in the question, x and z will also take only three cases as per y being 0, 1 and 2. Although we were not asked those 3 triplets, but what I need to do is, I need to find how many, then the number of solutions of the system. So I'll say 3 solutions, because y takes 3 values, correspondingly x and z will also take respectively 3 values each. Well, in that case, I'm having 3 solutions. So if I'm asked how many solutions this system of equations contains, where it had infinite solutions, but we imposed certain conditions, after that imposure, it will have only 3 solutions. Did you get that part? One mistake we committed here, although it's not a mistake. We were not asked the value of lambda and mu, nor I needed to solve it for lambda and mu, because lambda and mu were not needed in solving this particular question. As you all must have noticed, I did not use lambda or mu anywhere in this particular question. So lambda and mu, I think, as per my knowledge, were not needed as far as I think. But if lambda and mu were needed, we might have to do this, which I have mistakenly done, I believe so, because lambda and mu were not needed at all. Without lambda and mu also, we could find it, because I needed to solve these two equations only. From there only, I could find the value of z in terms of y, and then replacing the value of z here, I could find the value of x in terms of y. And once you have found x and z in terms of y, by using this inequality, we could get the answer. By having this thought in mind that x, y, z are integers, I could get the values of 3 values of y, integral values of y, corresponding to which there will be 3 respective values of x and z too, which means only 3 solutions. So lambda and mu were not needed to be explored in this particular question, even despite that you could have found the answer. Although, to ensure that it has infinite solutions, these two would be true, that yes, lambda should have been minus 17 and mu should have been 45. That is what is needed to be done. So I hope you have understood Cramer's rule, the different cases, the unique solution, infinite solutions, no solutions, and how does it get applied. That all is very well understood by you all. Let us move ahead with the next concept here. Now, what all other category of questions can be formed based on this particular concept? Let's explore that part as well, so that we can actually consolidate this particular portion, so that if any question is asked from this particular topic, you would be able to do that. Not just that, what J is mostly fond of is homogeneous linear equations. What do they do here is they basically give you again system of equations, but previously when we were dealing with the constant terms d1, d2, d3, this time instead of the constant terms they give you 0, 0 and 0. So basically the constants are 0 now. Now what does it mean? It means now if somebody notices it with utmost attention, he or she may claim, sir, that in this particular case, do you not think that one of the solutions will be 0, 0, 0? What I'm trying to make you understand is that if x is 0, if y becomes 0 and if z becomes 0, this triplet here 0, 0, 0, which we are proposing in place of x, y and z would be the solution. I hope most of you are noticing if 0 into anything, 0 into anything is 0 into anything. So if I replace x, y, z by 0, that will represent a solution. So that's a solution. So yes, x, y, z, if all three become 0, they will satisfy this system of equations. So that's definitely a solution. So that solution which we are discussing, all three of x, y, z becoming 0, well, that is the case which is called in this particular language as a trivial solution. So trivial solution means that there is only one solution, which is the value of x, y, z, all three of them become 0. But, mathematically, there is a possibility that apart from x, y, z being 0, 0, 0, is there any other possibility as well? The value of a triplet x, y, z becoming non-zero and still satisfying this particular system of equations? If you haven't understood my definition or language or the interpretation which I have tried giving you, I'll try to make you comprehend with a different mindset. What I'm saying is, let's say at least any one of x, y, z is non-zero. Let's say, to make you understand, let me take an example. Let's say there exists a triplet xyz where x is 2, y is -1 and z is 0, let's say. So here I'm seeing at least one value of either x, y or z is non-zero. Well, in that case, if that also coincidentally or luckily happens to be the solution of this system of equations, then in that case, I won't be able to say that this is the only solution I had for this particular system of equations. Well, apart from 0, 0, 0, I had or I could find, let's say, one more solution which had non-zero values of x, y and z, or at least one of x, y and z. And if that is so, if something like that can happen, or if something like that happens, then what do you get here? You say in that case that here that at least one of x, y and z is non-zero, at least one of x, y, z is found to be non-zero, and such solution is called non-trivial solution. Now again, coming up with the direct conclusions which you should remember. Then how do we verify or validate whether it will have a trivial solution or a non-trivial solution? What does trivial solution mean? That 0, 0, 0 is the only solution. What does non-trivial solution means? Apart from 0, 0, 0, there could be some other non-zero solutions as well. So when do or how do we verify that it has a non-trivial or a trivial solution? Well, the idea is very simple. I hope you know, we defined delta. What was delta? Delta was the coefficient determinant A1, B1, C1, A2, B2, C2 and A3, B3, C3. All you need to find is solve delta. Find this determinant delta. You will always see it will be either 0 or non-zero. If it is 0, you will have non-trivial solutions. If delta is 0, you will have some non-zero values of x, y and z which will also satisfy this system of equations. But if delta is not 0, you will say that this system of equations has a trivial solution which means it will be satisfied by 0, 0, 0 only. X, Y, and Z would be 0, 0, 0, nothing else. First learning which I'm willing to verify here is that are you able to understand what are homogeneous system of equations where d1, d2, d3 become 0? And in such case, you will have either trivial or non-trivial solutions. So what JEE keeps on asking is questions on the homogeneous system of equations having non-trivial solutions. And there they ask you to put delta is equal to 0, and that's how your job is done. Always remember, such questions are very often, very frequently asked. This is one of those topics which again is, I'll say, one of the favorite topics of IIT JEE. They constantly keep on asking questions based on this. So remember this. This is again a very crucial topic. Yes. Proceeding ahead, what's next? What gets unfolded next? Have a look at this particular question where yes, JEE Mains in 2024 itself has asked a question on system of equations having a non-trivial solution. And yes, we can see D1, D2, D3, the constant terms are 0, which means system of homogeneous linear equations. And how do we verify it has a non-trivial solution? The delta should be 0. Although I'm not asked to verify it, but I need to find the values of alpha for which this has a non-trivial solution. Now, how do we find that? Let us work on that. How do we do that, students? I hope you remembered delta should be 0. Now, what is delta in this case? Here in this case, if I start working on delta, I will get the value of delta as delta is the determinant of the coefficients of x, y, and z. So, coefficients are 1, 1, 1. The coefficients of x are 1, 1, 1. The coefficients of y are root 2 sine alpha. Then we have cos alpha. And next we have sine alpha, right? What is next? The coefficients of z are root 2 cos alpha. Then we have sine alpha. I hope I'm using the correct sign scheme. Yes, but with cos alpha, I should put a negative sign. So minus cos alpha. So this is the delta we have. Now this delta should be 0 in order to have a non-trivial solution of this system of homogeneous linear equations. Now how do we do that? So I will apply two operations here. The two operations will be that on row 2, I'll be applying an operation row 2 minus row 1, and row 3, on row 3, I'll be applying an operation row 3 minus, let's say, row 2. So these are the two operations which I'm thinking of performing. And let's see what do we get by doing so. Okay, so first row remains intact. So that will be 1. Then you'll have root 2 sine alpha, and then you have root 2 cos alpha. Right. What do we have next? Row 2 minus row 1. So 1 minus 1, that will be 0 here. And then you have cos alpha minus root 2 sine alpha. Okay, so let's keep it like this. Cos alpha minus root sine alpha. Right. I hope I've taken all the values correctly. Root 2 sine alpha, cos alpha, sine alpha, root 2 cos alpha, sine alpha minus cos alpha. Yes. So cos alpha minus root 2 sine alpha. Then you have row 2 minus row 1 in the third column gives you sine alpha minus root 2 cos alpha. I hope no confusions on that. Next, row 3 minus row 2. So that will be 1 minus 1. This should be again 0. Then you have sine alpha minus cos alpha. So this should be here sine alpha minus cos alpha. And then you have minus cos alpha minus sine alpha. So this should be your next result minus, I'm really sorry, it should not be minus sine. It should be minus cos alpha minus sine alpha. Anyways, that would have also remained same. And if it is a trivial solution, this delta should be 0. If it is a non-trivial solution, I'm really sorry, the delta should be 0. Now I'm expanding it with respect to column 1. I hope you can see when we are willing to expand it with respect to column 1, 1 into this into 1 into whole of this into this minus this into this will be done because rest of the elements are 0. So nothing much is needed to be done. So when you expand it with respect to column 1, what will happen? This into this and then this into this, right? So that product will be subtracted from this product. So a little, I would say, cautious you need to be while solving this particular portion. So let's focus on it. So cos alpha into minus cos alpha, that will give me minus cos square alpha. I hope you are paying attention to this. Then cos alpha minus sin alpha should be minus sin alpha cos alpha. Just take care of all these signs very well. I hope that is something which we need to be aware of. Then what do you have? The next part will be minus root 2 sin alpha minus cos alpha. So it should be plus root 2 sin alpha cos alpha. I hope no confusions on that. I'm doing it correctly. Yes. Then you have root 2 sin alpha minus minus plus. So it should be plus root 2 sin square alpha. So this should be plus root 2 sin square alpha. Let me just check the signs. Minus cos square alpha, then minus sin alpha cos alpha, then plus root 2 sin alpha cos alpha, then plus root 2 sin square alpha. From this product, I need to subtract another product. Now, what is that product? Let's focus on that part. See, what I get from here is sin alpha into sin alpha. That will be sin square alpha. No confusions on that. Sin alpha into root 2 cos alpha. It should be minus root 2 sin alpha cos alpha. Mind you, students, I hope there is no confusion on that. Next, minus cos alpha sin alpha should be minus sin alpha cos alpha, and then minus cos alpha minus root 2 cos alpha should be root 2 cos square alpha. So it should be root 2 cos square alpha, and this should be equal to 0. Let me just check this part. Sin alpha sin square alpha, sin alpha minus root 2 sin alpha cos alpha, minus cos alpha sin alpha, and then you have plus root 2 cos square alpha. Yes, because you need to be very cautious and alert. One single error with a sign will make your complete calculation go wrong, right? So be very alert, be very cautious while doing these kinds of calculations. Don't be in a rush, because with such part, if you do rush, if you try to be more fast, and that's where you commit the error, and all your efforts go in vain with such silly mistakes. So take care of it. Now, how do I proceed further? See, can I introduce this minus sign inside here so that the confusion does not stay here? So minus I'm putting or pushing inside. So when you push that minus sign inside, what happens? Let's have a look at that. See, when minus goes here, the results will be very simple, students. What will be the results? Let's have a look at that. See, this will become negative, this will become positive, this will become positive, and this should become negative. I hope there is no confusion on that. This was basically positive, so it will become negative. I hope no confusions on that. This was cos alpha, right? So this is what we are dealing with now. Now let's start putting the similar terms together so that we start getting the results. How do I begin with? I think I should begin with this. Which part, students? Which part I think I should begin with? I am seeing first of all this thing, right? See, I am seeing this particular part here. First of all, I'm clubbing sin square alpha with cos square alpha. Can you see that? Because sin square alpha plus cos square alpha will be 1, but it will be minus 1 because of this negative sign. So here, first of all, I'll be having a minus 1. I hope this part is very well understood by you all. What have I used so far? This part and this part. Next, what I am now having is, see, can you see that sin alpha cos alpha is getting cancelled by this sin alpha cos alpha? So I am removing this term because they are opposite in sign. Next part, students, can you see root 2 sin alpha cos alpha, root 2 sin alpha cos alpha will be 2 root 2 sin alpha cos alpha, and 2 sin theta cos theta is sin 2 theta. So 2 sin alpha cos alpha will be sin 2 alpha with the root 2. So it should be root 2 sin 2 alpha, right? So it should be plus root 2 sin 2 alpha. I hope there is no confusions on that. Now let me come to this particular part where we say that what do we do with this particular portion. I hope we are going great with whatever I've done so far. Now, when you deal with this particular part, root 2 sin square alpha, root 2 cos square alpha. So when I take the negative sign common, what am I left with? I think I am left with root 2 minus root 2 I'm taking common, right? So it should be cos square alpha minus sin square alpha. From this term and this term, I have taken minus root 2 common. So I'm left with cos square alpha minus sin square alpha. Another identity comes into picture, cos 2 alpha, because cos 2 theta is cos square theta minus sin square theta. That's exactly what is happening here if you take minus root 2 common. So with that minus root 2, I'll have cos 2 alpha, right? So with this minus root 2, I'll have cos 2 alpha is equal to 0. Let me just check all these signs first of all, because we have moved from one page to another. Cos square alpha, sin square alpha made it 1, but because of minus 1 it became minus 1. This 2 root 2 sin alpha cos alpha should be plus root 2 sin 2 alpha, and there we had this sin alpha cos alpha got cancelled, and there when we took minus root 2 common, it was cos square alpha minus sin square alpha, which made it cos 2 alpha. I think we are going great. Let us proceed further. From here, what do we have? From here we have root 2 sin 2 alpha minus root 2 cos 2 alpha is equal to 1. What I do next is I divide both the sides by root 2. So when I divide both the sides by root 2, I get sin 2 alpha minus cos 2 alpha is equal to 1 by root 2. I hope there is no confusions on that. Now what I do next is I should have divided it by 2. Okay, now I'm dividing it by root 2. So I'm dividing both the sides by root 2 and trying to convert it into sin A cos B, cos A sin B. I hope you remember sin A plus B or sin A minus B, like that will be created. So I'm dividing it by root 2. So what happens there is that this becomes 1 by root 2 times sin 2 alpha. This becomes 1 by root 2 times cos 2 alpha, and 1 by root 2 into 1 by root 2 is 1 by 2. Now what is the advantage of doing this? See, either I can make it as sin A cos B minus cos A sin B, or sin A sin B minus cos A cos B, whichever suits you. I think sin A cos B minus cos A sin B will be simpler. So this, if treated as sin A, it should be cos B. So this is cos pi by 4, right? So this is sin A, which is sin 2 alpha. So this here should be cos pi by 4, right, students? Similarly, this should be cos A, which is cos 2 alpha. Then this will become sin B. Sin B is 1 by root 2, so it should be sin pi by 4, which is equal to 1 by 2. This I'll deal with later. Now, what do we have next? Sin A cos B minus cos A sin B, sin A minus B. So it should be sin A minus B, which is A minus B, should be equal to sin 1 by 2. That's 30 degree. So sin pi by 6. So it should be sin pi by 6. Now we'll talk about the general solution. I hope you know that if I were to give you that sin theta is equal to sin alpha, the general solution is given by theta is equal to n pi plus minus 1 to the power n alpha, right? This is the general solution here. So how do I write the general solution in this case? I hope you have the theta, you have the alpha. So while comparing this, I'll get 2 alpha minus pi by 4. 2 alpha minus pi by 4 is equal to n pi plus minus 1 to the power n times theta, which happens to be pi by 6. I hope there is no confusions on it. Now I'll start putting different values of n and I'll start getting the results. So first of all, if I put n is equal to 0, what do I get? I get 2 alpha minus pi by 4 is equal to, this is 0, which means 1. So this should be pi by 6. So 2 alpha here is pi by 4 plus pi by 6, which when added, I hope you know that pi by 4 plus pi by 6, the LCM will be 12, 4, 3. So this should be 3 pi, 6, 2. So this should be 2 pi, and here it is 2 alpha. So 5 pi by 12 when multiplied by 2 in the denominator makes alpha as 5 pi by 24. 5 pi by 24 looks like something between 0 to pi by 2. Yes, 5 pi by 24 should be a value between 0 to 24, and that's our option B, 5 pi by 24. I hope you must have understood whenever alpha is 5 pi by 4, because alpha is supposed to be between 0 to pi by 2. This system of linear equations, homogeneous system of linear equations, will have a non-trivial solutions, which means apart from x, y, z being 0, 0, 0, there could be some other solution as well. Well, that other solution we were not supposed to find, but we were supposed to find in what scenario, under what case, this system of equations will have a non-trivial solutions, and that's exactly what we have figured out. Are you realizing determinants, trigonometry, both are clubbed? So this is what JEE does to you. So you cannot just always say that a particular chapter is most important or more important and that can be done and that will be suffice. What you need to understand is that you got to study all the chapters. So once you have studied all the chapters, then they merge all these chapters. So concepts are merged from different chapters and then they are asked. Let us move ahead. If you have understood how to deal with Cramer's rule, how to deal with homogeneous equations, then let us proceed further with the next part where we explore some more remaining few concepts of this particular chapter, such as how do you differentiate a determinant. First of all, sir, Are you not happy? Were you not satisfied that we have already learned differentiation? Now you want us to learn the differentiation of determinants? Yes, that is also something very crucial. Questions are asked on it, and it is one of the most important concepts you got to learn. It is not just another concept you're supposed to learn, but this concept will actually help you in solving a lot of other questions very easily. We'll of course understand it through some demonstrations, but as of now, let us understand how do you differentiate a determinant. Let's understand that X part first of all. Let's say I'm given a determinant delta X. So here it is not just another determinant, rather this is an algebraic determinant which has terms or elements in X for a while, let's say. So it has different functions, a1x, a2x, a3x, b1x. So all of these are terms in X, x square, e to the power x, sin x, log x. They are functions in X basically, right? So all the elements are here are functions of X. All the 9 elements of this third order determinant, 3 by 3, 9 elements, right? Now, what if I were to find delta dash x? How do you find delta dash x? How do you find the derivative of delta x? All you need to do is, how do we do that? First, I keep these two rows intact and differentiate the first row and write it here. So a1 dash x, a2 dash x, a3 dash x, and the remaining two rows will remain intact. Plus, what I do next is I keep the first row and the third row intact, and then I differentiate the second row. So b1 dash x, b2 dash x, b3 dash x, whereas the first and third row remain intact, unchanged. Plus, then I keep the first two rows unaltered, a1x, a2x, a3x, b1x, b2x, b3x, and I differentiate the third row, which is c1 dash x, c2 dash x, c3 dash x, and I add these three determinants. The result which we receive will be the derivative of delta x. Sir, can we not simply expand delta x first and then differentiate? Yes, you are allowed to, but that simple question they won't be asking. So they could be asking you a question where differentiation of determinant will be required, and how do you do that? You simply apply this particular process. Sir, you have done it row by row. Can we do it column by column? Yes. What does it mean? It simply means you differentiate first column, you keep the two columns intact, plus you differentiate the second column, keep the first and third column intact, plus you differentiate the third column, keep the first and second column intact. So that can also be called a valid differentiation of a determinant. I hope this part is not confusing at all. You're able to digest how to differentiate a determinant, and if you have understood that part, I'll try and make you understand this particular part with an example. But before that, there is a corollary which I wish to explain. This is something which IIT JEE asks. Of course, differentiating a determinant will be a very cumbersome process, so they actually simplify this process. They don't give you the function of x in all the row or on the columns. What they usually, I'm not saying this is what they always say, always do, or always ask, but this category of questions are more frequently asked on differentiation of determinants. How? Let's have a look at that. What they do is they give you just either one row or one column in x, and the other two row or other two columns are given as constant terms. So whenever such a delta x is given, do you realize what will be delta dash x? I hope you're realizing. If I were to find delta dash x here in this case, what am I supposed to do? I will differentiate first row first, then I'll keep the other two rows intact, so that will be delta dash x, plus differentiation of second row. Second row being constant will give 0, 0, 0, and any determinant having all the elements 0 in any column or any row will make its value 0. So that second determinant will be 0. Similarly, plus when you are writing the third determinant in this delta x series, where you will be differentiating the third row C1, C2, C3, that will again be 0, 0, 0. Other two rows, whatever they may be, but the derivative of third row will be 0, 0, 0, and again the value of that determinant will be 0. What does it mean? It means that delta x will be this only. So this is the category of questions which they usually ask, where they give you delta x. Two rows or two columns are kept constant, and one row or one column is given in terms of x. So when you're willing to find delta dash x, all you need to do is just write these two rows as it is and write the derivative of it. Let's say I'm asked delta 2x, which means second derivative of delta x. All I'll do is I'll find the second derivative of this first row while keeping that second and third row intact or unchanged or unaltered. So I hope you're understanding. If I'm asked the nth derivative of delta x in such scenario, all I need to write is the nth derivative of first row while keeping the other two rows intact. Did you get that part? I hope there is no confusions on that. You are very much comfortable with this. Let us solve a question and understand it more clearly. Question asked by JEE Mains in 2024. What does it say? This is asking you something. This is asking you something based on what is given as the value of yx. So yx is given, and again the very straightforward example is that only first row contains terms in x. The other two rows are completely constants. How do we deal with that? I think the part is very simple. The part is very easy. First of all, let me find dy by dx. Okay, so I am working on dy by dx. I hope we can find dy by dx. How do I do that? I'm really sorry. I often forget switching this particular part. So I'll write dy by dx here. I hope that doesn't confuse you all. So dy by dx will be, I hope it is very simple for you now. What will I do? Only first row will be differentiated. Second row and third row will remain intact. We have already learnt why and how. So first row, sin x, the derivative of sin x is cos x. You already know it, I believe, because you have studied it in physics. The basics of physics also teach you the basics of derivatives, although we also learn it: differentiation, integration, application of derivatives, area under the curve, indefinite, definite integration, and then differential equations. Entire calculus is there to get unfolded as of now. But yes, I hope you know these basics. The derivative of sin x will be cos x. Similarly, the derivative of cos x will be minus sin x, and the derivative of sin x plus cos x plus 1 will be sin x will be cos x will be minus sin x, and 1 will be 0, while keeping the other two rows intact. I hope you are getting it. So the other two rows I'll write later, but now let us work on writing d2y. Let us work on writing d2y by dx square. What am I supposed to do for that? Basically, now redifferentiate it. Again, the other two rows are constants because they are what? They are 27, 28 and 27, and then this is 1, this is 1, and this is 1. So I need not bother about that, because again, if I redifferentiate it, these two rows will remain as it is. I need to simply differentiate the first row. That will be the derivative of this. That will be the second derivative of y. That's exactly we are trying to find. Now, how do we do that? The derivative of cos x, it should be minus sin x. So I'm writing it here, minus sin x. The derivative of minus sin x, it should be sin x. The derivative of sin x is cos x, so it should be minus cos x here. So I'm writing minus cos x here. Here, the derivative of cos x will be minus sin x. It will be cos x. So minus sin x minus cos x. So I'm writing minus sin x minus cos x here, right? And this d2y by dx square is needed to be added with y, because this is what we are asked, right? So I'm adding it with y. Now what is y here, students? Y we already know. We are given this y, right? So we are given the y. Y was this. So again, if you are paying attention here, my dear students, are you not seeing something very relevant, very crucial, very simple here? What is that part, students? Again, if I have some space here, I would like to write y as well. So I'm writing y here. So y is given as sin x, then we have this cos x, then we have sin x plus cos x plus 1. We are running short of space, so I'm writing y here. I'll write it somewhere else. Okay, so I'm writing it on a different page. I am wanting to save some time because I don't have the tool to pick it up. So how do I remove it? So I'll try to shift it a little on the left hand side. How do we do that? Okay, so this got removed. It doesn't work. So let me use some other tool, right? This, I think, will it work? Okay, this doesn't work. So simply I'll have to write it, right? So this is what is it, students? It is basically d2y by dx square, right? So this was d2y by dx square. Now, what do I do next? I'll write y here. What is happening here? I need to write y here. So I'll be writing y here on this side, right? I hope you are comfortable with that. So what is y? Y is already written there, but to show it to you more clearly, I'm writing here. I hope you are comfortable with this. Sin x cos x, then you have sin x plus cos x plus 1, right? then you have 27, 28, 27, then you have 1, 1, 1. Now, have we learned the addition of determinants, the subtraction of determinants? All you need to have is at least 2 rows or 2 columns should be identical. Then only determinants can be added or subtracted. So that's exactly what is happening over here. Second row and third row are identical, which means first row, the elements of the first row, the corresponding elements of the first row can be added. Yes, that's exactly what I'll do. So how do I do that? Let's have a look at that part. See, here I'll be writing sin x minus sin x, that will be 0. Cos x minus cos x, that will be 0. Sin x plus cos x plus 1 minus sin x minus cos x. So only plus 1 will be left there, and the other 2 rows will be simply 27, 28, 27, and there you have 1, 1, 1. So this is the value of d2y by dx square plus 5, but this is not what we are asked. We are asked the value of the determinant, which you know by knowing the expansion of the determinant, and I'll expand it along with the row 1. So row 1 says this, which I need not mind. So plus minus plus. So this will be plus 1 into what do I have? Get rid of the column and the row which is contained by 1 or which contains 1. So I'll be left with 27 into 1 minus 28 into 1. So 27 minus 28, which we all know is minus 1. Minus 1 into 1 should be minus 1. So minus 1, option A should be the correct answer over here. Did you all get that part? Sir, I don't want to do all this. Can I first expand yx by using the expansion of determinants and then solve it? You are free to do that. But do you still not think that this was easier? This was way much easier. And that's exactly what I was trying to explain, that determinants, differentiation should also be learned by you all. In the same fashion, when we were doing differentiation of determinants, they ask you questions based on integration as well. So I'll simply be teaching you how do you integrate a determinant, and then we'll come to the part where you understand sum of determinants. These are the 2 parts we are left with, which will conclude this chapter possibly. How? Have a look at that. So how do you integrate it? So first of all, delta x will be given in terms of 3 elements are there in x, and then the remaining 2 rows have constant terms. Or any column may have terms in x and the other 2 columns will be constant. So how do you write the integration of delta x? I am writing the definite integration. So I'm putting some limits a to b delta x. Well, it will be a to b integration of f of x, integration of g of x from a to b, integration of h of x from a to b, and the other 2 row remains as it is. I repeat, the constraint, the limitation here is that only one row or only one column had terms in the variable x. If it had, let me read this particular line so that you get more clarity. If in a determinant, the elements of more than one column or rows are functions of x, then integration can be done only after evaluation or expansion of the determinant. For example, if here also I had a function in x, which means 2 rows have functions in x. In that case, I am not supposed to follow this process. In that case, I am supposed to first of all expand the determinant, then only I'll be able to integrate it. So integration of determinants is possible only when either one row or one column has terms in x. That row or that column will be integrated with respect to x, other 2 rows will remain intact, and that's how you'll get the integration of delta x. If it is definite integration, you are supposed to put the limits, that's perfectly fine. But the limitation, I hope, will be remembered by you all very strictly, that if there is one more row or one more column which contain a variable term, then you are not supposed to do that. Then you will first of all expand that determinant and then integrate it. I hope you are understanding this constraint. That is a very minute point, a very fine line gap which is not understood by most of the students, and they commit errors on it. The same way we understood derivative, the same way we understood integration, the same way we should understand summation as well. Sir, can summation also be applied on determinants? Trust me, it can be applied on determinants. In the same way we applied integration, summation also works. I hope you understand summation is something which will study under the chapter sequence and series. There you'll get more clarity. There will discuss a question based on this particular concept. Don't worry about that. But right now what you need to understand, again, The same way we are, let's say, given some functions in X, let's say we are given some expressions in R, but this expression in R should be given in either one column or one row. The same way integration happened, right? And if I ask you summation of delta R from the value of R from, let's say, 1 to n or whatever it is, then I can apply this summation individually on these elements, and I can keep these two rows, the constant rows, intact. But I hope you're understanding the limitation here. The limitation is pretty simple, that terms in R should be given either in one column or one row. If you didn't get this part, I'll explain it with more clarity with one example so that you understand it very simply. For example, let's say you're given delta R, which says determinant, which is, let's say, 1 R square, then you have 2, 3, 4, let's say, and then -1, 0 and 5, right? And let's say if somebody asks you, this is the example I'm creating or making right now, summation R is ranging from 1 to, let's say, 5 of delta R is what you're supposed to ask. So first of all, check or assess. Does this determinant contains terms in R in either one row or one column? Yes, that is given. Only first row contains it. So summation can be applied. Sir, what if any other row or any other column contain terms in R? In that case, expand it first, then apply summation. But here I can apply the summation directly on the first row, and second and third row can remain unaltered. So summation can be written as summation over 1, summation over R, summation over R square, and these two rows will remain as it is, 2, 3, 4, -1, 0 and 5. That's exactly what I'm trying to make you understand. Now, how do you deal with this summation part? Don't worry about it. If you don't know it, we will study it while we study the chapter sequence and series. So don't worry about that. But I hope, how do you apply summation and integration on determinants? That's a little tricky part, and that's where students commit the error. That's where students make the mistake. I hope you will remember this particular part and won't commit any such error on that front. If I could conclude whatever we have studied so far, then my conclusion will be simple. You should know how to expand a determinant. You should know what are the minors and cofactors of a determinant. You should know the different properties of determinants. You should know where all places where this chapter determinants, the concept of determinants can be used, especially in coordinate geometry, vectors, and a lot more places. Along with this, the system of equations, how did we deal with it? The product of determinants, row by row, row by column, column by column, column by row, or some crucial results such as differentiation of determinants, integration of determinants, summation of integrations. Along with one very important concept on which questions are every year asked, which are solving homogeneous linear equations, non-trivial solutions, that category of questions. So I hope we are very much clear with this particular part, and you know that in this one-shot series, we are covering every single chapter with utmost details in a comprehensive manner. Along with these videos, you are also getting the handwritten notes. These PPTs in a PDF format are also provided there to you, along with practice sheets, which are called the DPPs. All of this is already available for you on our PW app, an amazing platform where a lot of students are already preparing for different competitive exams. The link to our application is already given in the description. You can click on it and access this entire content on the app. With that, I think you have gotten a complete clarity on this particular chapter. Let's meet in the next video where we'll be discussing matrices in a more detailed format. Thank you so much. Take a good care of yourself. You have been a great audience.